Let's get started with our session for the day. Okay, good morning. So today is all going to be about low energy transients, and by low energy, by no means are they any less exciting. So we'll hear first from Matteo, who is one of the co-organizers of the school, and Matteo got his undergrad degree at PISA and was a PhD student at Utrecht, and then was a postdoc at KITP, and since then has been a research scientist at the CCA. So Matteo works on a broad range of topics in stellar astrophysics, all the way from stars inside AGN to binary stars, and he'll be telling us today a lot about the end stages of the lives of massive stars. One quick announcement, please be here at right at 11 after the coffee break. We have a special announcement. So just after a coffee break, we'll try to be here back at 11. Okay. All right. Any questions?
What's the special announcement?
Oh, you got to know at 11. Yes. All right, take it away.
All right. It's special because you have to wait to know what it's going to be, Andrea. Okay, so I'm very excited to have a long conversation about massive stars and their end stages. First, I wanted to tell you a bit about this slide. So yesterday, Brian came and had this very fancy quantum magazine illustration. Let's see if I can get this. And so I said, I also need to have a fancy illustration for my talk. And so, I did what you do this day, which is to go to ChatGPT and copy paste the title of my talk and ask it to make a beautiful illustration of outbursts and late stage of massive stars. And this is what it came up with. I thought it was hilarious. So I decided to keep it. So it's probably a new model for producing runaway stars, who knows? But today we're going to talk about stars, and as I mentioned, end stages. So first, let's get back to stellar physics 101 just for a second. The life of a star is a continual struggle between its gravitational force, trying to collapse it, and the pressure gradient supporting it. So this is the definition of hydrostatic equilibrium. Because gravity is a central force, stars tend to be spherical unless they rotate very, very fast. And the story of stars, stellar evolution, is literally the story of this constant struggle between gravity and the gradient of pressure. Because stars are hot, they compress gas, they tend to leak energy out into the stellar medium. So they lose energy. Their luminosity is a rate of energy loss. So something I gotta give. And the energy is supplied by nuclear burning in the core, but nuclear burning can only proceed as long as you have enough fuel to support it. And every time you run out of fuel, the core, what it does, it just reaches a new state of hydrostatic equilibrium by compressing, reaching higher temperature that enable you to burn heavier fuels, produce more energy that keeps the star in hydrostatic equilibrium for some more time. Literally, this is all is there in terms of simple picture for stars. The very fact that you moving from one fuel like hydrogen to helium and so on means that there is a compositional change inside the star. And that's really what drives stellar evolution. Okay, so I just want to remind you, set the stage of a couple of important facts about stars, about their time scales that are relevant for looking at stars and stellar evolution. The first one is the shorter time scale that you usually encounter when you think about stars. It's called the dynamical time scale. Is the time scale at which the star will react to a perturbation of the hydrostatic equilibrium. If you slap the star will ring for a little bit, and those waves that propagate through the star are sound waves, and the time scale for those waves to propagate is fairly short. In the case of the sun, for example, is 0.5 2 days. So just a matter of less than an hour. Now, of course, stars also are hot. They have the thermal energy content. And so they're also in thermal equilibrium. What is thermal equilibrium and what is the deviation from it? If you were to turn off nuclear energy sources from the core of a star, the star will have to vacuum its thermal energy, and that will take some time. Early on, when people were trying to understand how the sun shines, one of the ideas was maybe the sun is just like a very hot ball of gas, which is just contracting. And people realized that could not be the answer, because that time scale for contraction at a constant luminosity is called the Kelvin-Helmholtz time scale. You take your internal energy and you radiate away, you get a time scale. You know that internal energy, the real term, is a half of a gravitational energy, and so you get this time scale here. And it turns out that for a star like the sun, this is not that long. It's of order of tens of millions of years. Now, people already realized late of the 18th century that you have fossil that date probably much older than that. And so the sun must have been around for much longer. That would push people to think about other ways to power stars. Quantum mechanics arrive. In fact, people figure out that you could do nuclear fusion in the core of stars. And so when we talk about nuclear fusion, which is the longest time scale, most of the time we'll see a situation where that's actually not the case. For your run-of-the-mill star in the sky, this is the longest time scale available, is the time it takes to run through the nuclear energy. So the fuel, the energy provided burning the fuel in the core of the star or somewhere in a shell, for example. And for the sun, this time scale is order of 10 billion years. So this hierarchy of time scales is usually found in stars, definitely for stars in the main sequence, that is when they're burning hydrogen. And so the nuclear time scale is much, much longer than the time it takes to stay in thermal equilibrium and the time it takes to reassess its dynamical hydrostatic equilibrium. Okay. I'm gonna get back to this. Now, okay, one important thing that we need to remember is that fuels don't all burn equally. Different fuels burn with different properties. It takes the energy, nuclear energy generation depends on the density and the temperature, most importantly on the temperature, with different power. For example, for the sun, energy is supplied by what's called the PP chain, which is a series of nuclear reaction that takes 4 nuclei of hydrogen and makes 1 of helium. And this PP chain has a fairly shallow dependence on the temperature. But if you go to more massive stars, for example, stars more massive than about 2 solar masses, actually 1.1 or 1.2 solar masses, sinks in the core start working differently. You can actually burn hydrogen to helium by going through a different chain of nuclear reaction that use a catalyst, the CNO, and this one actually it's much more dependent on temperatures. The gradient, the stiffness as respect to temperature is higher. In general, as you burn heavier fuel, this tend to be true that your nuclear energy generation tends to depend more and more steeply on the temperature. This is an important consequence that we'll talk about. Okay, so just to remind you a little bit, again, stellar structure 101. If you go from very low mass stars to more massive stars, at least on the main sequence, the internal structure tends to change. Stars that are low mass stars, like a fraction of the mass of the sun, let's say 0.3 solar masses, they tend to be fully convective. If you increase the mass and so the temperature of the core, you start having a situation where the core is radiative and the envelope is convective. This is the case of our star, the sun. And then if you go to higher mass eventually you start producing a convective core during the main sequence and mostly radiated envelope, except for thin convection zone that we're not going to bother too much about today. Do you know why this is happening? You know why the sun doesn't have a convective core, but a star of 2 solar masses, for example, does? Andrea?
Is it the difference between CNO and PP?
Yeah. So remember this, the steepness of the nuclear energy generation with temperature means that the CNO cycle concentrates on energy production in a much smaller region. So the temperature gradient that it produces is steeper, which allows to create the condition for energy to be needed to be transported out via convection. So the amount of energy you distribute in a small part of a star is so much that radiation cannot take it out. And so you need to turn on convection, which is a hydrodynamical process that allows you to move energy out toward the surface or in part of the star faster. Okay. The star we're going to deal with are pretty much most of the talk, except toward the end where we might talk about common envelope events, are usually of this kind on the main sequence, massive, with a convective core during the main sequence, as they evolve to do other things. So let's talk about massive stars. One important thing to remember about massive stars is they're a little different than our sun, in the sense that if you look at the profile in the density temperature plane, which kind of tells you a little bit where the gas lands in terms of property of the gas. Once solar mass star is kind of well approximated by an ideal gas, and with a adiabatic exponent of 5/3. But if you move toward more and more massive stars, the stars tend to be more and more luminous. Radiation becomes more important. And in fact, the contribution of radiation pressure to the total pressure becomes non-negligible. In fact, for the more massive star, like 100, you see they lie on top of this line, which is the line of radiation domination. If you go even more massive, and we'll talk about that at some point, you might end up in a situation where the star, it's so radiation dominated in some part, it becomes unstable. This is actually going to be an important aspect of trying to understand where certain type of mass losses outbursts might come from. And since I mentioned mass loss, you probably heard about this, and massive stars tend to lose their mass in some ways. These processes can come from a different number of modalities. The one that we do understand is actually the one that matters the least, unfortunately. It's line-driven winds, a beautiful theory that connect the outer layer of the star interaction with the radiation field. You can literally look at the interaction between light and atomic structure. Light is absorbed, kicks some momentum into the other layers, and then you can slowly drive a flow, and you can drive a wind. And there's actually one-dimensional solution to this problem. There are been developed in the 70s. They work fairly well. In fact, the observation of wind mass loss tend to be reproduced by the model within a factor of a few, which usually have to do with some non-one-dimensional structure in the wind, something like wind clumping, for example. And the important part about line-driven winds, which depends on the metallicity, the reason for this is simple. If you want to interact with matter and you're a photon, your best bet is hitting on something that has a lot of electrons around it. You want to, because that implies that there's a lot of possible jumps in the quantum state of the electrons that will lock into energy band where you can actually deposit your energy. In a sense, like material become more opaque to matter that way. So this line-driven wind tend to be dependent on the abundance of material like iron, because iron has a lot of electrons. And so you end up having a strong dependence on metallicity. So line-driven winds tend to be strong in the local universe at small metallicity, but they go away, or at least become very weak as you go to the early universe where metallicity is very low because we didn't have many stars changing the abundances yet. Okay, so but stars, and these are line-driven winds are important if the star is relatively hot because you need to have some of this species to be partially ionized. If the star moves to a region of the HR diagram where it becomes cooler, that's what stars tend to do. They evolve past the main sequence and they want to move to the red. That's because mostly they usually they have a large amount of hydrogen in the outer envelope, and hydrogen, as the star expands, recombines, provide a lot of capacity, which leads to an expansion of the star. It's a bit more complicated than that, but you know this. Stars move to this part, and they become red supergiants if they're massive. At that point, they also lose mass via cool winds. These are poorly understood. There's no real theoretical model for first principle to reproduce the observation of cool supergiant winds. In fact, this, the type of recipes that we use in stellar evolution codes come from observation. We still don't know if these winds are occurring in a continuum way or they're dominated by periodic outbursts of some kind and maybe mediated by things like pulsation that we'll see are common in stars like red supergiants. And then there are other type of massless, like continuum-driven winds and eruption, which is something that we're particularly interested in today because this might deposit on a short time large amount of material around the star, reshape the circumstellar medium, which provide interesting feature if the star explodes in such environment. Something that we know, it's interaction with local environments. So we're definitely interested in this type of mass loss, also because to drive this kind of large amount of mass loss eruptive events, probably you also need to become very bright and luminous. So you might have a transient associated. And so the hope is that maybe we can observe these things as they erupt.
Matteo?
Yeah.
So these, okay. Yeah, I was going to ask about these line-driven winds. So
yeah,
most of the heavier elements are like generally in the inner part of the star. So are these winds like driving material from the inner part of the star?
Yeah, it's a good question. So yes, that's true. The star, turn itself into heavier things in the core, but a local metal in local universe, you have some amount of iron in the mixture from which the star is made, and that's enough. You don't need that many atoms. Of course, they have so many atoms of hydrogen for every atom of iron, but the atom of iron is what really drive the absorption process and then redistribute the momentum. The atom of iron gets a kick and then, bounce on the other atom of hydrogen and collectively transfer momentum to the other layers of the star, which are then accelerated out. But yes, indeed, the metallicity dependence is fairly steep. So eventually, if you run out of iron, you have to rely on things like carbon, nitrogen, oxygen if you have it, and that's much less efficient. If you don't have that too, there's actually no way to accelerate these winds, so that those winds go away. That's kind of the idea of a population tree stars. Very early on, maybe they don't have line-driven winds and they have to rely on other modality to lose mass, if they do at all. We don't know. But the point I wanted to make with this plot, which comes from a review from Nathan Smith from 2014, is that the winds that we actually understand are kind of the one that really don't matter. I said that at the beginning, but in the sense, they matter because you lose mass in this modality for a long time, in the main sequence, for example. But eventually, for the more massive star, the one that might do some interesting or more wild things, the mass that is lost at least close to the star is going to probably come from some of this zoo of phenomena that are very poorly understood. So LBV eruptions, maybe mass transfer in a binary system, and we'll talk a little bit about these things. Okay.
Matteo, did you say what cool winds are? Or is that just like an
Yeah, no.
observational definition?
I mentioned red supergiant. Everything that is lost when, in a sense, the hydrogen recombine at the surface of a star, you get like cool or cool enough. Like, let's say anything that is like probably happening at temperature lower than 10,000 Kelvin on the surface, I would call it. So I would call it like cool winds. So yellow hypergiants have this type of behavior. Red supergiant for sure. Again, they might drive winds a different way. We just don't know how.
Right.
Yeah.
I had a related question because
Yeah.
when you say doesn't matter, I mean, I have seen scenarios where binary evolution is trying to produce a compact, binary black hole, and then you would end up at a stage where you have stripped stars and the binary sort of widens due to the mass loss.
Yeah.
So that is line driven, right, from the helium stars.
Right,
Would
right.
you say that's reasonably understood, or is that
So that
in this
depends.
category of?
Okay, so Brian is bringing out a point that an extra important feature of losing mass on the main sequence when you even if the amount of total mass maybe is less than what you might lose later, is still important because it might drive important phenomena that lead, for example, to interactions. So in a binary system, your balance of orbital angular momentum, it's dependent on the way you lose mass from the star. So depending how you're losing mass, you might lead to shrinking the binary or actually maybe expanding it, depending if the mass loss is concentrated on an equatorial flow or polar flow. But that's important because most massive stars, I'll make that point later, turn out to be in binary or even more, maybe multiple systems. And some of these might be close and already try to interact on the main sequence. So this wind, at least at Solomon Listi or in the local universe, might have important impact in determining quantitatively which star might interact. Good point. Yeah, Andrea.
So for the Wolf-Rayet stars, is that just like a super special case of line driven, or is it just the
Same theory.
radiation?
Yeah, you can apply the same theory. It turns out that you're very hot actually for a Wolf-Rayet star, even hotter than the main sequence. So you're bang on into the regime where you can apply the line driving theory. There are some subtleties. The winds are so dense that the photosphere of the star ends up in the wind. So if you look at the Wolf-Rayet star in some of this situation, you actually never see the surface. You see somewhere in the wind. And so the fact that the wind is optically thick has some implication on how you model it. But the theory of how you transfer momentum is the same.
But just follow-up question, is it special just because you're so high mass and so luminous and so radiation pressure dominated that this works, or do you also need some metallicity enhancement in order to actually get to a
Good point.
Wolf-Rayet?
Yes, you have both. On one hand, your luminosity is very high. Your gravity is higher. So actually the escape velocity is higher. So those winds tend to be faster and more dense. Those things are also very compact. And at the same time, Wolf-Rayet stars tend to be enhanced because, well, they're kind of the reveal core or reveal inner region of a star that right down undergone some evolution. So they can be rich in nitrogen, oxygen even, and that can have an impact on the metallicity and the abundance of the surface. So when you do your calculation of how much momentum can you exchange, you need to account for the fact that your composition is different. But the calculation is, for all purposes, the same. Okay. All right, let's talk about late evolution of massive stars. This is where the fun begins. This plot is a trajectory of the core property of a star as function of its lifetime. And it's showing central density and temperature. So it's really like the core of the star. This is a 15 solar mass model. Ends up here and start igniting hydrogen in the core. You see that's the typical temperature for a few tens million Kelvin. That's what you need to ignite hydrogen in the core of the star. And then it continues, to get denser and hotter until you run out of hydrogen. There's some contraction happening there, and then you ignite helium, and you keep going. It's a triple alpha now. And eventually you get to ignition of carbon. Then later phases, you do neon, and oxygen, silicon, and you end up with iron. Now you can burn anything anymore. Okay, so one thing I want to tell you is like how long this process lasts. Well, you probably heard that massive stars live for a few million years, sometimes depending on the mass, from tens to a few. And that's mostly telling you what's the lifetime in the main sequence. Let's look at the lifetime later. This is again for our fiducial 15 solar mass model. This is the temperature ignition of different fuel. You can see the temperature is going up as you move toward heavier fuels. Note after carbon, you don't ignite oxygen, but you ignite neon first. Anybody knows why? What's special about oxygen? Oxygen is very stable. It's has its double magic number, and so it takes more energy to actually start fusing oxygen than neon, even if neon is higher up on the periodic table. But so you start with neon, and eventually you go to oxygen, and then finally go silicon. The one thing that I want you to look at is a time scale for the duration of this process. So it's like 10 million years on the main sequence, about 10% of that on the helium burning, and the rest is like 1,000 years for carbon burning, 1 year, a few years for neon and oxygen, 18 days for silicon. This is kind of surprising, isn't it? Are we talking about things happening on days for a star? Never heard that. So why is that? What's happening here? So why do duration of late burning phases gets progressively shorter? And this is not just happening for 15 solar mass, it's happening for every massive star that we want. Any ideas? Yeah.
If you like draw the binding energy per nucleon, you get a big spike when you go up to helium, but it sort of is flattening out the whole time.
Good. So okay, great. So that's a piece of the puzzle. I'll say it's not the most important one, but you're right. The burning time scale, again, it's your energy available divided by the rate at which you're losing your energy. And the energy available is given by the energy you can extract from your fuel. And that depends on the binding energy per nucleon that is available. And as we just heard, the difference between two isotopes in different chain of burning tend to get progressively smaller. You can see the distance, this plot tend to flatten, meaning that eventually you extract much less energy from burning one light fuel into a heavier next fuel until you get to iron where you can't really extract any more energy, and that's why that's where stars gave up. But I would say that this is actually not the most important reason for that. There's another more important reason why this evolutionary phase tend to get shorter and shorter.
Steep temperature dependence for your reaction rates.
Right, but in the end, that's true. But in the end, this is what really determines the burning time scale. So you have some energy. It doesn't matter how maybe you extract. If your temperature steepness it means that you just need like a smaller region in the core to get the energy you need to sustain the structure. It's just that what part of the star you're going to use to do that. Yeah.
High temperature, you also have high energy. It's just high energy, so that
right.
Probability is,
but in the end, what you need to do is just sustain your cell structure. And so what was going on?
You have fewer total nuclei in a smaller area, so how long it takes them all to run into each other is shorter.
I think that's true, but it doesn't change, I think, any of this. Okay.
We have higher luminosity, so the
Okay.
time scale increases.
It's true. Luminosity is getting higher. But I want to show you something.
But can I add a brief,
Yeah.
brief clue, which is
Yes.
luminosity cannot exceed the luminosity we see, right? You can't exceed the Eddington luminosity, right? So that can't keep getting higher. Anyway,
Right.
that
That's
was my
true.
clue.
Brian's point is that to go from 10 million years to a few days, it means that your luminosity will have to go up so much that you probably exceed the Eddington limit. So the star will not be stable if that was the case.
Do you lose more, do you emit more neutrinos?
Right.
With those?
Okay. This is the trick. The star is actually losing a lot of luminosity. The light that is coming out is still the light it takes to kind of like keep its structure in place, because the photons are doing the work of keeping star in isotonic equilibrium. The star, unfortunately, is losing a lot of energy because the photons are staying in, but neutrinos are just lost once they're emitted. And for the sun, the amount of energy lost in neutrino is very small. But as you get to higher and higher temperature, neutrino processes start becoming very important. Eventually, they exceed wildly the amount of luminosity comes out of the star. This is actually something maybe you haven't appreciated before. I kind of didn't when I stumbled into this, where I started thinking a little bit more deeply about this. There's a complicated plot, but this is an HR diagram. So it's luminosity, so the volumetric luminosity in photons coming out of the star, and there's temperature, see different masses. And you can see up here, the range actually luminosity for 15 solar mass model here from the main sequence to where it dies is actually very small. So the luminosity doesn't change that much. But look at the neutrino luminosity. From the main sequence of a massive star, it goes up 10 orders of magnitude eventually as it evolves to later stages of burning. Just because the temperature gets so high and neutrino production becomes very favorable, and neutrinos are just lost. And the thing is that the star is losing all this energy. What it can do, just burn faster, burn faster, burn faster. So basically, it's a very leaky process of trying to keep hydrostatic equilibrium in a situation where all your energy is lost as you produce it, and only a small fraction goes into luminosity. So very inefficient nuclear reactor in that case, in terms of sustaining the cell structure, and that's why eventually these late phases of burning are so short. Note that because of this, nuclear burning has to go very fast. A lot of energy is, and that actually has implication for the type of internal structure you can also create, because you start creating these very strong nuclear gradients, temperature gradients, which drive convection faster and faster as well inside star. This is going back to what Ani was saying. It's like you have this very region of strong energy production, but also very, very strong associated gradient temperature that's drive convection that gets faster and faster. And that's something that we're going to talk about in a second, because it matters for some models of potential pre-supernova outburst. Okay. Right, so this is your two effects: energy available going down, luminosity going up, and this one dominates. Yeah, so the other thing to know is that actually the temperature at which you ignite your fuel, it's really like the crossing of the neutrino losses, which tend to dominate eventually, because at some point, what you want to do actually is not anymore like kind of sustain hydrostatic equilibrium. You want to compensate for your losses from neutrinos. And so that turns out to be exactly what is happening. These are the nuclear burning energy generation curve, and this is the neutrino losses. And you can see that the temperature of burning corresponds to where it intersects this curve. Okay. Okay, so when I started studying stars for my PhD, the whole idea when we were running models was that once you get to some of these late stage evolution, because those nuclear burning phases are so short, you kind of can forget about what happened at the surface of a star, because remember, the time it takes for the star to adjust its thermal equilibrium and its appearance, if you want, so how much it takes for photons to propagate outward and affect the properties of the envelope, it's the Cantiello timescale. But this Cantiello timescale becomes eventually longer, becomes longer than the nuclear timescale, only in this very latest phase of evolution. So that hierarchy that we talked about at the beginning is violated in this late phase evolution. So pretty much around carbon burning, one can kind of forget about the surface of the star, just simulate the core, and the prediction will be that the star would never move in the chart diagram past that point. So whatever you do in the core, it doesn't really matter. That was a kind of a paradigm. You evolve until carbon burning, forget about the envelope, just evolve the core, something like this. Anything happening in the core cannot influence the surface appearance of stars in the last year before they explode. Then the era of surveys came. People started, developing a better understanding of not only the supernova zoo, but also of things like what happened to supernovae or progenitor supernovae right before they explode, and what's going on with their circumstellar material. So just to remind you, this is it's a very broad stroke, like look at the supernova zoo, but just entertain me for a second. Low mass stars, single stars, they retain their hydrogen envelopes. When they explode, they make two plateaus, so the hydrogen rich, maybe two Bs. Increase in the mass, you get to 2L. Eventually, you get to this regime where stars might explode in a situation where they lost all the material, and then this type 2N, and stand for narrow narrow emission lines from the interactive region, came about. And of course, you can also lose your mass up here, either via winds or interaction with the binary, and then you remove your envelope, you end up with a Wolf-Rayet star. When you explode, you got a type 1bc, which has or not helium in the spectrum. In terms of how many of these things we do see, type 2Ps account for about 50 to 70% of core collapse supernovae. The 2N are fairly rare, but not too rare, 5-10% of these core collapse supernovae. And the type 1bc are about 20-30% of core collapse. Now, the fact that the 1bc are such a large fraction already tell you that actually this idea that maybe these are only coming from the more massive star that were able to lose mass via winds. It's not good. There's something else going on. In fact, I think to make that number work, you need to assume that some of these Wolf-Rayet are actually created by binary interaction, so strip it, and that reconcile potentially the number. So that we'll get back to binarity and interaction later. But just don't give you the impression that I believe that this one single star picture is the right one. This frozen in envelope paradigm was fairly accepted. This is from a beautiful book from Andrea Matteo in 2009, talking about massive star, the focus on rotation. But this paragraph toward the end really carry on this idea. The difference of timescale between the envelope and the core implies that the envelope can no longer adjust its thermal structure to the fast central evolution at the surface. L and effective temperature no longer change from the carbon burning phase. The changes are generally small, even from the end of the helium burning phase, whatever. The stars stay at the same place in the chart diagram until the supernova explosion. Then, as I said, the surveys came about and kind of changed really the picture. Observers started saying, where's stuff happening? And while at the beginning, there was thought, maybe there's some weird situation where something else is going on. Eventually, more recently, I think some of this systematic exploration show that some of these outbursts in some classes of supernova are actually quite common. And some of these things might happen even in stars that we thought would be super mellow, like, run-of-the-mill, low-mass red supergiants. So the things that we're looking at are like precursor, rather than minus 13 magnitude, 3 months before the supernova explosion in about 1/4 of type 2N supernovae. So probably, this is associated with the fact that type 2N has all this CSM nearby. So kind of understandable that they might have some of this supernova outbursts. But this was not predicted by the model. And then, these things might be common. Maybe not all core corrupt supernovae do this outburst before, but there is clearly association with mass loss, and even in low mass supergiants, as I'll see in a second. So, this is the typical situation. Like, I think some of these are type 2N, and this is kind of a red supergiant that recently was observed that also shows some level of activity before supernova explosion. And you can see here, these are like observation before the star went off, which is something we've only been able to do in recent time. Before it was more like, trigger when you get triggered, but you don't observe things for a long time before. So you can see this level of variability before, at least, days or months before the supernova. So it's very interesting. Again, not predicted by the models. And some of this variability, we think, reshaped the CSM. And this is also observed via flash spectroscopy. If you have material around the star, not too far, moving at low velocities, when the shock breaks out, it photoionizes some of this cooler, denser material, which then shines back and creates a visible emission line peak, which can tell you information about how much material is around the newly formed supernova and what's its density under certain assumptions. And so you can recreate a little bit the history of the mass loss rate, so when it happened and how much of it. So recently was this, of course, work from Brian and Tatsuya, showing like the ability to potentially create a model to, model some of this, the emission from this material launch before some of these eruptions. So using some of this, some of the theory that they developed, for example, for also for luminous red novae, as we'll see later, you can kind of create light curves. And so people have used this to try to reproduce these outbursts. And it turns out that you can, if you, for example, inject energy at a certain time into the envelope, like you do an energy deposition of some amount of energy in the envelope of the star, you let it run out, the shock created, then you can kind of reproduce the light curve properties. It's harder if you try to do this with a kind of with a constant wind, as coming from some eating process. But I think, there's a lot of details, possible extra features that might be important in this type of modeling. Just to show you that people are trying to do these things. And I would say there are a couple of ideas of how to drive this type of mass loss, which we'll look more in detail in a second. Instability in nuclear shell burning and wave heating coming from very strong convective nuclear burning in the center of the star. The reason why I put this early and not before we talk about the theory is that I just want to say that this model exists and people have kind of used them to make prediction for their Rubin. And so the interesting, exciting stuff, I think, for us is that if these models hold, and they can reproduce some of the observations, so we hope that they are a good template for this, you can try to simulate how many of this precursor event you might be able to see, and the answer is hundreds per year. And so that's, I think, an interesting landscape that we're going to be able to explore with Vera Rubin. And then there is this case that I mentioned earlier of a red supergiant. So for type 2N, I think the expectation at the same we're doing wild stuff toward the end of the evolution is kind of like emerging and becoming the new paradigm. But I think people are still holding on to the idea red supergiants are very tame. Turns out they're not. Most red supergiants now showing not only some structure material very close to the surface, there's some like halo surrounding most red supergiants that has impact, for example, for the way that the shock breaks out, but also some of this emission pre-explosion. This is this situation for the red supergiant that I talked about earlier, so 2020 TLF. And you can see this precursor emission before the supernova. You can see also there is material around that probably was ejected via this type of variability. And you can see the narrow lines from a photonization / spectroscopy that give you some of the more information about the CSM. So its velocity, you can see it's fairly low, and its density and the position. And so what is going on here? We'll get to this with possible ideas. But this is just to show you again the ability to see these things. I think that the interesting thing is that Vera Rubin is going to be able to see this stuff up to 100 megaparsec. This is typical. Red supergiants are typical. So this is like expected to be a 10 to 12 solar mass progenitor. So kind of like run-of-the-mill massive star explosion. Yeah, so the properties that are inferred from this observation using some modeling are, as I said, 10 to 12 solar mass progenitor. The mass loss rate prior to the explosion, so in this like few months before core collapse, is of the order of 10 to the minus 2 solar masses per year. Now, if you remember the plot I showed you, there's very few ways to drive mass loss to that rate. Definitely not line driving. This is above what line driving can do literally physically. So we know it's not what it is. This is also hydrogen rich, so we don't expect that. So this is something else. And the amount of material that was expelled is not very large, but remember, this is a 10 to 12 solar mass star. But it's still like, a few percent, up to maybe 10% of solar mass. And the other thing that was observed is that the star seems to be inflated. So it seems to be a little bigger than you would expect if you were just running a model of the red supergiant of 10 to 12 solar masses.
What about the temperature? Surface temperature of the star?
I mean, I don't remember. I think that they have, let's see, they have the black body temperature as of the fit during the pre-emission, pre-supernova emission, and it's of the order of, I would say, 4,000 Kelvin, something like that.
And the model without shocks would predict what?
So I'm going to talk about the model a bit more, but there is a model from Jim Fuller. We're going to talk about this type of wave heating phenomenology that in a second, more physics, but jumping ahead, if you have some source of heating coming from the core that deposit energy, you can affect your model. You can inject energy, expand the other envelope, maybe drive some kind of wind at the surface if enough energy is deposited. This is what this like black line is doing. And I think what it does, it can match the radius at the right time of the model. I think this starts around the right time. It's only heating when it needs to be heated. But it cannot match the luminosity of the model. So it seems like there's something missing. I'll get back to that in a second. Right. So going back to some of these models of precursor in red supergiants, there's some work that's been done, again, doing agnostic envelope in energy injection in the model, tuned to reproduce the observed CSM properties. So you can see here, there's a shock breakout, and then this emission due to recombination of hydrogen as the material expands in different light curve as function of time. People use this to, again, make some some forecast for the visibility of this very dim. This is like, now it's a dim precursor compared to what we were looking at before. And this can be still seen by Rubin beyond 10 megaparsec at least. So this is work from Tsuna, 2023. So I think this is also fairly exciting for the prospect of studying some of this early stage of pre-supernova emission and outbursts. Okay. Okay, we talk a lot about some of these observations, kind of like enigmatic, a little mixed up. So let's talk about what possibly is going on. What is breaking this assumption of frozen in envelope? So let's start with waves. Turns out that convection excites internal gravity waves. I'll start with the simulation. Now, this sucks because it's going via Zoom, but trust me, what you're looking at is a simulation of a star on the main sequence in this case. So it's only relevant for demonstrating the physics. There is core convection here. There's hydrogen burning. And all this stuff that you're seeing outside is kind of like, this is a three-dimensional simulation. Is just a cut on the meridional plane. You can see all this structure. These are like waves, internal gravity waves generated by the turbulent convection. When I say gravity waves, what do I mean? A wave is response of a mechanical system to a perturbation. You know this. Usually you need a restoring force. And for gravity waves, that restoring force is buoyancy. So the example of gravity waves you've seen them everywhere, like there's some type of gravity waves are surface waves in the ocean. Sometimes you've seen these things in clouds formation. Those are mapping gravity waves in the atmosphere. For stars, it sucks that it's not really running smoothly. But anyway, this simulation is really showing the evolution of core convection. You can see the turbulence, and the turbulence really excite the propagation of this internal gravity wave with some spectrum and amplitude. I want to linger too much on this equation. And I think the one that you want to remember is this one. So the luminosity, the amount of energy per unit time that goes into a wave depends on you might imagine, the amount of luminosity that you have in the convection. Understandable, it's the maximum one you can extract via an efficiency parameter that depends on the Mach number. That's interesting. So very low Mach number convection. So Mach number means like the convective speed is much lower in this case than the sound speed. So for low Mach number, that's subsonic convection, very subsonic convection, the amount of wave that you extract is not very high. You still do extract some, and there's a power spectrum of the wave. There's some theory has been developed in the years about this, and some of this theory has been validated via numerical simulation. But the idea is that you know how much energy at different frequency and spatial wavelength you deposit. When you think about this L in this equation here, in the spectrum, of course, you're thinking about harmonic, spherical harmonics. So, you know, like low L, meaning like large scale dipole, for example, L equal 1. And if you go to higher L, it means like more and more nodes, if you want, on your spherical harmonic. And so higher, smaller structure in your perturbation. Now, remember this. The duration of the nuclear burning for this late stage of burning goes down the luminosity diffusion goes up. Remember, you see how much you need to produce in luminosity to supply energy to neutrinos. The star is kind of staying the same luminosity in photons, and that increased amount of luminosity drive faster and faster convection. This is an important point. Your Mach number tend to become larger and larger. So toward the end, a phenomena that during most of the life of a star only extracted a very small amount of energy from convection now is tapping into larger luminosity with a much higher efficiency. So if you look at the amount of wave energy you can extract as you move toward late phase evolution, it becomes larger. So this is a Kippenham plot. It's more complicated. It's time until core collapse. And this is mass of the star. So we're literally looking inside the star in a 1D profile and evolving in time. And this different color zone are mapping the luminosity produced by waves in different part of the star. And these are actually, this is starting at core nuclear, carbon burning. You see there's a core convection here. It's exciting some amount of wave. That is a core shell burning, neon core burning, neon shell burning, oxygen burning, oxygen shell burning, finally silicon burning. And you can see the trend here is also like convective envelope and helium shell, but it doesn't matter. The amount of luminosity in the waves increases toward the end because of that increasing Mach number. So turns out that once you excite the waves in this deep region of the star, these gravity waves, what they want to do, they want to propagate outward. Can they do that? Well, it's complicated. The gravity waves can propagate in a radiative zone. And then when it encounters a convection zone, depending on the structure of the star, more complicated than that, it either gets transmitted to a sound wave and propagate outward, or maybe it never makes it out. So depending on the structure of the star, you can leak some energy from these gravity waves into sound waves that then propagate outward, and they either dissipate via some mechanism, for example, wave breaking, and deposit their energy. Turns out that in some of these models, if you do the work of following the waves within the cavity, within the cell structure, you can deposit in the envelope, which is where we care about, up to 10 to 48 ergs of energy in the last months of the or year before the explosion. And this is an interesting amount of energy. So this is the original work from Elliot Quater and Josh Shieldy in 2012, who kind of proposed this idea first. There was a lot of follow-up work from Jim Fuller and his group. And I think where we stand here is that this is definitely providing some source of energy deposition. The details are complicated. But in the most optimistic case, you can actually change the property of the star and inflate the star and even drive some amount of mass loss. An example of this phenomenology. So this is time until collapse. And you can see this is a red supergiant model where, so a typical star, where in the last 2 years, the radius of the star changed substantially due to the injection of energy via these waves. There's also some interesting hollow cavity that's been created by the energy deposition. I don't know if that's stable or not, something I'll ask Jim about, but the important point is that even in a 15 solar mass red supergiant, this energy deposition was able to change the structure in just a couple of years before the supernova went off. So in general, for a typical 2P progenitor, so round mean of red supergiants, Jim's work predicts models, luminosity excursion, an impact on radius and envelope structure, might be important for the light curve, and then might explain mild pre-supernova outbursts in red supergiants, leading to observed flash spectroscopy. But the ejecta mass is predicted to be small and with not very high velocity. So this might be consistent with some of the observation, but marginally the velocity tend to be a little larger. I'm gonna skip this. It's a little technical. Let's see how much time I have. Yeah, let me maybe spend a couple, because I gave you a little bit this idea, this explanation of the waves propagating out. I didn't really tell you exactly what happens. So let's maybe focus a little bit on this diagram. It's called propagation diagram. It's a tool that is used in astroseismology. It's really telling you a way to look at how waves of different type can propagate in a star. The star is basically a three-dimensional musical instrument. And so you can divide in different cavities that can sustain different type of oscillation. If your star, for example, has a radiative core, like in this case, the star, spoiler alert, is a red giant, so not much to do with the star we're going to look in a second, but give you a good idea of how this thing works. So the radiative core, and in the radiative core, you have this red region called the G-mode cavity, which is basically defined by a specific characteristic frequency called the Brunt-Vazila frequency. You probably heard that name. Nobody knows how to write it down correctly. But it is pretty much the frequency of oscillation of a piece of plasma in a star, an element of stellar material, in a radiative zero region, so a stably certified region that is undergone a perturbation. So you try to push it down, and the piece of plasma wants to go back and oscillate, a little bit like a buoy at the surface of the ocean. So like these waves can only live with frequencies below this and in regions confined by this Brunt-Vazila frequency. So this example, G mode can live here and just propagate at this frequency between here and this part of the star. At this frequency, it can go a little further out. The other important characteristic frequency is called the Lamb frequency, which is this blue curve. It's nothing else than the inverse of the sound crossing time. So it's pretty much has to do with sound waves or P modes. P modes because the restoring force is a gradient pressure. This is how we're communicating right now with acoustic waves. And an acoustic wave can only live at a certain frequency for regions above both the red and the blue curve. So at this frequency, the sound waves can only propagate from here to here. So for example, if you excite a gravity mode in the core of this star, and you hope to pass some of the energy to the P modes that then reach the surface, because the G modes never make it to the surface, you have to go through this tiny little region, which is called an evanescent zone. This is really like the same thing as channeling in quantum mechanics. Your amplitude, the amplitude of the eigenfunction decrease exponentially in that region. So of course, the larger this zone, the less energy you propagate. If you're down here, for example, there's no hope you're gonna channel any energy to the P mode cavity. So you can see from this that the details of how much energy you can drop into the envelope depends carefully on the details of your internal structure of the star. And this is an easy structure of the star. The one that we're going to deal with, it's something like this. This is a 15 solid mass star doing oxygen burning. Again, radius, log radius on the x-axis. Yes?
Can I ask a question about
Yeah.
the radius plot?
Yeah.
So I'm going to have some structure of the star where the Brunt is something and the Lamb frequency is something else. And so then if I like ring that part of the star at a certain frequency, the type of wave that I will get will depend on where it lives in this diagram, basically.
Correct. And it depends where you're perturbing the star. Of course, this is the instrument as it was built. To play a sound, somebody has to play the instrument. so as to deposit energy into the instrument. So you can do it two ways. You can like smash the surface of the star and create sound wave, and then hope that it's gonna, like eventually drop some energy into the core and excite G modes up to certain frequency, some certain amplitude. Or you can excite inner region of the star and hope that the G modes propagate into the and couple to the T mode and drop enough energy to make something that is observable on the surface. Turns out that in the red giants, this is what happened. You play the envelope via turbulent convection because the star is a red giant, so there's turbulence, and turbulence excite some of these P modes, and eventually you leak enough energy to excite the G modes in the core. And those G modes probe the property of the core, that then information is brought back to surface, and you can study the core of a star via this technique. That's pretty neat. You can study rotation of the core, even the presence of magnetic fields, pretty cool stuff. In our case, it's the opposite. We have oxygen burning, for example, in this situation. It's convective, high Mach number. It's exciting waves at certain frequency, which depends on the turnover frequency of convection. And waves try to propagate outward, but now they have a difficult trip to make. They propagate into the gravity zone. So this is again the brown Vasella frequency cavity. You can see here it's excited and it goes very well. It has a little bit of a tunneling situation going on here. So at this point, the amplitude is going to be lower. Propagate here again, and then now you have a lot of tunneling, and eventually the amount of wave that the energy that makes it here can couple to outgoing sound waves. And these might steepen and deposit energy somewhere in the envelope. So all this process needs to be tracked. And it depends a lot on this like Wiggles curve that depends a lot on how you treat convective boundaries, mixing processes, and it's all one dimension. I'm just saying that this is hard. I think Jim did an incredible job in trying to come up with a systematic exploration of some of these models, but I think there's a lot of uncertainty. When you do the math of calculating the excitation and the propagation and the dissipation of this wave, this is the luminosity that you can inject. So this is the nuclear burning luminosity that's coming from MESA and the stellar evolution code. And these like blue lines are coming from this extra energy that is deposited as heat in the envelope. So this is all the energy that makes it. So you can see that from the fraction of energy that was in convection, that luminosity, you going many, many order of magnitude down because of a number of things. You have Mach number, it's giving an efficiency factor, then you have to transport via the tunneling, and then eventually you get here. But still some interesting amount of luminosity that is deposited, increasing toward the end of this life of a star, which is what we want. And this can actually have an impact on the property of the envelope and can launch waves, like in this case. You can see the wave is launched at the bottom of the convective envelope, and it moves outward, propagate, and I think there is this shock breakout due to this neon burning pressure wave created by the gravity waves excited by neon burning in the core of the star. Pretty cool stuff. And one effect is this radial inflation that you can see just about 1 year. This energy just puff up the star by a factor of 0.5 or something like that. And finally, putting the coffin, the nail on the coffin of the frozen in envelope paradigm, this is the HR diagram of that model. This is where I think this is pre-neon ignition, not even carbon burning. So just like a few years prior to collapse, that's where the star was, and then where it's exploded. So a big excursion in both luminosity and temperature. So the envelope fell the core. It's just that the transport, it was not thermal, it was just a wave. So waves are able to couple mechanically the core to the envelope on a much shorter time scale, which is close to dynamical time scale. So that's a cool thing about this model. And last thing I want to say about the wave driving is that because of the different structure that you might get if you have a supergiant hydrogen rich or a stripped hydrogen poor, you actually turns out that the strip star are better ways to extract energy and deposit it into the other region by proxy of an easier travel for the waves. Again, this is the point where you're exciting the wave in this case. This is it's a convective shell in this case. So you have a convective shell here, this neon burning, exciting wave that propagate outward. And you can see that for the hydrogen-rich model, you have a large amount of tunneling and you have to do, much larger than in the model with a strip star. And so it turns out that the strip star model are much better suited to show some activity before supernova goes off due to this wave energy deposition mechanism.
Matteo, so
Yeah.
can you say more about what sets this these gravity cavities versus this tunneling region, this structure?
Yeah, the brand Vasana frequency has two components. One is due to composition and one is the thermal stratification. So it's really like, it's the stratification of stratification means like things are stratifying gravity. They want to stay in a radiative region that way. And how stiff the stratification is depend on the thermal properties of the plasma and the composition. For example, if there's a steep compositional gradient, it's like water above oil. Your ability to push the oil down is much harder because, so it's a stiffness boundary. So your Brandt Vasila in that location is affected steeply by the composition, just to give an example. So all this structure here, all this like weird wiggle have to do with the fact that in one-dimensional model, we treat mixing as diffusion process, but it's one-dimensional. And so the composition might have between grid points, like transition that are like, large, not super smooth. We don't smooth out too much of this. And so you can have structure in the Brandt. Astroseismologists hate this because this makes, creating models of the oscillation of the star in the cavity much harder. And so there are ways to, help with that by doing more smoothing, for example. But really what's happening depends a lot on the reality of what kind of mixing processes exist in three-dimensional structure. And these are 1D models, so not much we can do. Okay, so to wrap up on wave eating, since I have like about 17 minutes left, I think it's a promising avenue to explain some of the pre-supernova activity occurring in partially stripped stars, and also maybe announced CSM in low mass supergiant giants. The other point I'm going to make in a second is that maybe wave eating in the end is not really what is driving the muscles, but it might be setting the stage for something else to happen. Because if you maybe deposit enough energy to change the star structure by expanding it, but there's a timing that you're doing. So that's the important point. This only happens very late in the evolution of stars, and it's timed to be happening a few years or a few days even right before the star explodes. That's the important point. So you have a way maybe to expand the star at the right time, and then something else happens. And what that could be, for example, you might lead to enhanced binary interaction. Imagine your star was already in a very close to another star, and now you're expanding it. All of a sudden, you're able to induce some mass transfer, maybe it's dynamical nature, that's going to reshape the CSM very rapidly right before the star go bang, because you timed it right, because the star timed it right for you. So maybe what's happening is that this is setting the stage for enhancing binary interaction right before collapse. The whole idea of binary interaction always didn't sit well for me in this context of pre-supernova, because it's like, what are the chances that the star is really the period of the star is right, so that it will only interact right at that time when it's about to go supernova. this kind of, I think, alleviate a little bit that problem, because provide a little bit of a clock. I think the physics of wave driving is very sound, to the idea at least. This got to happen in some form. Many of three-dimensional modeling, by the way, of shell burning now exist, and they all show this dynamics. This waves exist, are created in numerical simulation. But both the excitation and propagation of waves depends on uncertain aspect of stellar structure and wave spectrum. So I think that that's where the details matter. And I think, like it's really hard to be very quantitative. So in the end, maybe not too surprising, there are currently no wave-driven models that can fully match observer pre-exposure activity. So this sentence was taken from a paper discussing this. So without this part, so I think it's not too surprising, but they were complaining that some of this model don't reproduce very well. I think it's already great that they reduce some of the aspects. So I wouldn't throw away the model just because we can't really get all the features as in the observations. Okay, I mentioned binary interactions, so let me spend a couple of slides about this. We discussed at the beginning that binaries and stellar interaction are very common especially in the regime of massive stars. There's this paper from Yuxana in 2012, which came up with a survey of spectroscopic survey of stars and massive stars, and figure out that given the binary properties observed, pretty much only 1/3 of stars are actually, or massive stars are found to be single, or at least that effectively evolve as single stars. All the other one will undergo some kind of interaction with a companion. Interaction could be a merger, or just accretion spin-up, or a common envelope, or just envelope stripping, which is, as we discussed, might, create some of the Wolf-Rayet stars that we observe. Turns out it's even more complicated than that, I think, because it's not just binary, it's multiplicity. This is a paper from Stella Offner, Max Moll, and Kathleen Kratner, and shows as function of the mass of the primary. So, we actually care about stars in this regime. What is the fraction of not just binary, but multiplicity? So, and it turns out that that's very high. So stars are not just surrounded by companion, but multiple stars most of the time, especially in the high mass regime. Okay, so with that in mind, this point I made about potential late time expansion as a way to trigger some late time binary interaction becomes even more interesting. So what might lead to late time expansion is a number of ideas. One is what we just talked about, this wave heating. But some of the stars do that normally, actually. So this is a model of strip stars close to core collapse. These are helium stars, so there's only helium left. So that's why they're so compact. It's a Wolf-Rayet star. And as you see, as function of time, there's ignition of carbon and then neon here. And you can see that after carbon ignition, there is a expansion. But then later on, very close to the stellar death, there is another expansion happening. This has to do with the internal structure of like convective shell overlying convective nuclear burning, or nuclear burning in general. It's called the mirror principle. And so it leads to some expansion that might be of interest, again, for reigniting mass transfer in a previous binary system. And so I think Jim and some collaborators look at this a bit more quantitatively by really looking at the idea of putting a binary situation like this and then injecting energy in one of the two stars, so it expands enough to fill the Rush lobe. And this is time with the late phases of evolution, and seeing a little bit what the CSM structure might look like, which might be the CSM where you later on explode. And again, this idea that overall wave eating or shell burning in strip start can lead to cell expansion time shortly after core collapse. This can in turn enhance the chance of late time cell interaction. We can reshape the pre-supernova CSM with implication for the resulting supernova properties. Okay, so a few more mechanisms that might be relevant to the idea of driving pre-supernova mass loss mechanism. I'll try to be quick here. One is pulsational instabilities, and the other one is burning shell instabilities. When it comes to pulsation, I mentioned earlier that red supergiants are actually affected by pulsation. Those are radial pulsation excited by the kappa mechanism. So due to the opacity of hydrogen in this case, there's some work some time ago where we look at the stability of some of these red supergiants, finding that at high enough luminosity in the model, at least, those stars those models tend to be unstable to radial pulsation. This is what it looked like in a one-dimensional model. This is the radius and Mach number of the oscillation. And so you can see that for 25 solar mass red supergiant, you get this growing amplitude pulsation as a radial mode with increasing Mach number until Mach number equals 1. So you start creating shocks. The model was stopped there. But the idea was that this might actually lead to some enhanced mass loss. So imagine you have your run-of-the-mill normal red supergiant mass loss, and all of a sudden you start oscillating like crazy, creating shocks that might lead to what we call the super wind phase. We try to implement this in the models, and this can enhance the mass loss rate by several order of magnitude. Very hard to time it right at core collapse, I would say. But again, this is another mechanism that might trigger some binary interaction where, you know, the star is now oscillating at large amplitude, maybe catching up with a nearby companion. The other pulsation instability that I wanted to briefly mention, because I think it's important, even if I think it's only pertained to the realm of very massive stars, so the rate of these things can't be too high, is periinstability. This is, again, an important feature of massive star that evolved to very high core temperature. Eventually, if the thermal energy in the core becomes comparable to if the frequency of the photons give energy to photons that's comparable to the thermal energy you need basically enough energy to activate electron-positron pair production, and this requires temperature of about 10 to the 9 Kelvin. This is basically fixing the energy requirement to the rest mass of the electron-positron pair. And so this is important because at this temperature, because the star is radiation pressure dominated, really the gradient in pressure that is keeping the star in place is provided by photons. That's the feature of the core of these massive stars. So if you have a mechanism to decrease the number of photons, that mechanism is going to start to decrease the amount of pressure, which leads to an increase in temperature, which feedback on your ability of create more positron-electron pair, which decrease again your amount of photons, which run away into a destabilization of the star.
Don't the pairs also supply pressure? I mean, sources of opacity and pressure?
I think it's very low compared to the photon because you're radiation dominated situation.
The pairs are not fully relativistic at these temperatures, so they're not. Yeah, I mean, you're also you're basically you're turning energy into rest mass of these guys, so it's wasted energy that's not available to provide pressure.
Right.
Another way.
Right. Yes, true. So so what happens actually, you can drive a dynamical instability. Again, for dynamical instability, we look at the adiabatic index of the gas, which measure the responsive pressure to adiabatic compression. And stability requires the allobatic gradient to be larger than 1/3. Turns out that if you start creating a lot of these electron-positron pairs, you can drive gamma below 1/3 in large enough region of the star to satisfy this equation. And when that happens, you instigate a dynamical instability. This happens for large enough models. I can see here where the inner region penetrate this gamma less than 1/3 region. And eventually those models undergo what we call current stability, which can be of pulsational nature at the lowest mass where these occur, or can lead to complete destruction of the star at higher masses. The mass stability core largely determines if a star can undergo the current stability. And these are expected to come for very massive stars, especially in the local universe, but in the local universe, so those massive stars lose a lot of mass, so they never get to have CO cores large enough. So the rate in the local universe is expected to be very low, of order of 10 to minus 5, 10 to minus 4, the core collapse supernova rate. But this might be higher at low metallicity and in the early universe. We don't really know. Now, one thing that I wanted to mention about current stability supernovae, well, one thing I didn't say is that in the regime where the star is not completely destroyed, but you have this pulsation, this can lead to mass loss and variability. And this mass loss can remove enough mass to kind of bring the star to low enough mass so that you evade this region. So the star is moved out of this region, and the star still can survive and still collapse and form, for example, a black hole. So in a sense, this is this idea that you can remove star in a regime of mass bounded by this positional apparent stability edge, and the upper edge is basically bounded by stars are so massive that you can't really destroy them by injecting all the energy via nuclear deflagration. And so you get a regime where you expect no black holes to be formed out of this mechanism. So this is important because the prediction from this type of modeling, it's pretty sound, is that there should be no black holes formed by stellar evolution in the regime between 52 and 133 solar masses. This was a very specific prediction made by Stan Woosley in 2017. To his credit, more recent work has actually showed that that's a good assessment. Maybe this comes down by a few solar masses, but this makes a clear prediction for where LIGO, Virgo, and Cadrashu, which regime of black hole mergers masses the detector should see. And so now we have enough to see that actually we do have black hole mergers coming from black holes of masses that are high enough to be in that gap. And so the big question is, how did this black hole form? Open question, I think. Some potential modeling that are, circumventing this problem by dealing with a different environment for cell evolution, and multiple generation of black hole mergers.
So missing the most recent system, which is very interesting. But,
yeah, I think I took this yesterday from their website from Northwestern. I think they haven't updated.
yeah, the recent one has above 200 in total.
Yeah, it's true.
And it's more certain that the components must be in the mass gap, so it's a big mystery.
That's also a mystery how you form that. Yeah. Cool. All right. Want to spend a couple of words about burning shell instabilities. It's a little technical, but there's this idea that maybe another thing that can happen is that some of this late phase of nuclear burning in some models lead to flashes of igniting fuel in degenerate regions that can lead to liberation of large amounts of energy. This is the case of models between 9 and 11 solar masses. This is interesting because those are, fairly common stars, massive stars. IMF reward you there. And so this is a work from Stan Wissing and Alexander Eger in 2015. This is again a Kipperan diagram showing evolution the last year of stellar lifetime. To note, this is a off-center silicon burning, and this is also silicon burning. But you can see that we haven't seen off-center silicon burning before, and the reason is that in this situation, the core is degenerate, and so the ignition of the fuel happens not at the center, but outside. And the reason is that when you degenerate, you don't depend on the pressure. Temperature doesn't depend on the pressure. So compressing the core is not really change. The inner region doesn't really change temperature. And you have strong neutrino losses at that point. So basically, you're able to cool down this region and have a kind of a temperature inversion and have like ignition off center. And because you're igniting in a degenerate region, you also can lift a lot of energy, get a lot of energy by lifting some partially degeneracy. And this is like this off-center flash that you see here. Details are a bit more complicated. There is what's called a convectively bound flame propagating. I won't bother you with the details, but all in all, what they see in this model is the ability to produce inject large amount of energy very late in the stellar evolution, which might lead to some interesting outburst right before the supernova goes off. Finally, the last thing is hard disk structure. Again, a disk structure that we see in 1D, really like this stable hard disk, like boundaries of convective region well behaved. Do we capture those regions well? I think the jury's still out, but in the past have been work trying to simulate this region in 2D and now even in 3D. And people have proposed the idea that we're underestimating the amount of turbulence and entrainment of fuel, meaning like how much mixing there might happen between shells and mixing between fuels that can lead occasionally to potentially, injection of lighter fuel into very high temperature zone that might lead to generating large amount of energy and potentially outbursts again. And this will be a consequence of the hydrodynamics of and stability of the shells in late phase of evolution. Okay, I think I ran out of time, so I don't have much time to talk about common envelope events. Just kind of it's fine, but we will hear much about this in the afternoon, I think, from Viraj. Yeah, thank you for your attention.
Any questions?
So I think there was like this recent paper maybe a couple weeks back talking about some evidence for shell merger in the final hours of CAS A based on the distribution of certain elements. I don't know if you have any.
Yeah, so this paper from 2015 talks about CAS A. And they make some prediction for, they think, this could be a CAS A progenitor and this very late, very late like energy injection in the center silicon burning might lead to some mixing and unbinding of material that might reflect into the structure of the supernova and distribution of material in CAS A. Yeah, I didn't read the paper in detail, but I think that what was evident for me is the connection with this paper.
Can I ask, because you have other degenerate flashes in stars, like when you ignite helium burning, and people usually say it doesn't do anything.
I think it's wrong.
What?
I think it's strong. I think
Yeah.
it might do something. We do see some
Right.
changes in abundances of the surface. I mean,
Okay.
I think Josiah Schwab has a paper on that.
Sure.
Adam Germain has done some thinking about that. I think again, it's like, I think the amount of energy here is larger that you can inject, I think, to, compared to the binding energy of the star.
Okay.
So I think while for the helium flash is remarkable and can lead to some maybe wave-driven mixing or something like that, here it's really a structural question. I think the Stan claims that you have enough energy here, and you can see here, like the last little, so that black line here is the cumulative energy injected. You can see this like bouncing up. There's like this little bounce up there is at level of 10 to the 51, a few 10 to the 51 ergs, and it's really like happening, like hours maybe before the, or maybe a few days before the supernova. So that's
This is energy injected well.
This is the energy like extracted by this nuclear energy generation.
I mean, maybe to connect to the transients a little bit, there are these ILOT transients, some of which have very dusty progenitor stars, and there's been a long debate as to whether these are non-terminal eruptions or what electron capture supernova, whatever that implies, meaning this sort of massive star. Not that the supernova itself is any fundamentally different. So I guess I'm curious: is this thought of as a way? This is thought of as a possible way to make? Because if just hours, I don't think that's not going to produce a huge dusty.
So this is happening right above the electron capture supernova regime. So in a sense, here in this, the electron capture supernova regime is like 7.58 to maybe 9.5, and then above that, again, depends how you treat overshooting and all these things. But above there is this type of phenomenology of off-center successful ignition of. So this will make a core collapse, and it's just
make an iron core.
It's just the way that it gets there. It's this little slightly different because of this off center. And then you increase the mass, and this goes away completely because now you don't have this degenerate off center extinction anymore. But a lower mass than this, then you have the electron capture supernova realization that might be connected to the intermediate luminosity red transients.
But in terms of explaining why some of the intermediate luminosity red transients are so shrouded in dust, you'd prefer some kind of like super wind scenario? Or
those are super HEV stars that are very luminous HEV stars. So I would imagine they do what HEV stars do, more, and they lose. And turns out that they lose increasingly more. I mean, that's not I think that's not too different from the proposal that we have with Sunchul. That there's more luminous red supergiant. Eventually, they tend to have this pulsation instability enhanced the wind mass loss, and that might happen, year before, not at core collapse, but in the 100,000 years leading to core collapse. And I think the super HEV star is kind of the same. It's just like this more luminous HEV star. They undergo more of the same, pulsationally driven dust-aided mass loss. And then they do the electron capture supernova maybe into this, CSM.
Yeah, I think we should break there. Let's thank Matteo again. Okay, we are ready for the next lecture for today. So we heard this morning about all of the effects that take place at the end stages of massive stars, and our next lecture will be on a different class of low energy transients, which also have to do with massive stars. Andrea will be telling us about failed supernovae. So Andrea did her undergrad at UC Santa Cruz and got a PhD at Berkeley, and since then has been FRF at CCA, and is an expert in massive star evolution and well, some of the probably the most intriguing ways massive stars can die, and he'll tell us today about what LSST can do for this.
Thank you, Keisha Loy. I think you have to switch the camera. It's still showing the front. Okay, so given that this is a sort of observational summer school, I'm going to actually start with observations, and then I'll, on the chalkboard, do some of the theory. And so first of all, what do I mean by a failed supernova? So when people say a failed supernova, they're really talking about this sort of supernova mechanism that Jared talked about last week, where the iron core collapses from the size of the Earth to the size of, let's say, San Francisco in order of a second. This can release a huge amount of energy because the binding energy of the neutron star is 10 to the 53 ergs. But as you heard, the inner part of the core reaches sort of nuclear densities and it stops its free fall. So now you have the solid surface and the outer core is falling in and slamming into the surface, and you get this sort of standing accretion shock. And of course, it's this sort of neutrino-driven turbulent layer behind a stalled shock that needs to win out over the infalling ram pressure of the outer core in order for this core collapse to lead to a supernova explosion of the star. And we see lots of black holes that are more than 1% more massive than the most massive neutron star. So we know that there must be massive stellar deaths where a good chunk of the inner part of the star is falling in and becoming a part of this black hole. And so this, when people say a failed supernova, they're referring to these sort of black hole forming core collapse deaths where you don't drive an energetic supernova and the majority of the star is still bound and wants to fall and accrete. And the key question is, what happens to the rest of the star, and can you still have a luminous transient? Now, my focus today is really on the sort of red supergiants, yellow supergiants, so stars that, maybe start their lives below 30 or 35 solar masses. These, of course, are very important stars because they're the most common supernova progenitors. And we know that the deaths of red supergiants in successful explosions give rise to the most common types of supernovae, which are the type 2p. So just because our initial mass function falls off with mass, the red and yellow supergiants you really care about. Okay, and so the old thinking used to be, so let me start with this survey. So Chris Kachanik, you don't have to turn around yet, started this survey in 2018 where basically they were looking at 1 million red supergiants in nearby galaxies and waiting for them to disappear. So back then the idea was that the cores of red supergiants are very slowly rotating at the times of their deaths. So the core collapses in a failed supernova, you form a black hole, and you don't have enough rotation to say have an angular momentum powered transient. Like if, on the other hand, you had a rapidly rotating Wolf-Rayet star collapse, right? All that rotation, you get this disk, you drive this relativistic jet, long GRB, associated type 1 BC supernova. So this isn't going to happen in a red supergiant, not only because the core is slowly rotating, but also you have, 10 solar masses of envelope sitting on top of you that anything you drive from the center would have to sort of get out of. Okay, so the idea back in 2008 is that if a red supergiant had a failed supernova, it should just disappear. And so they just started this survey that's been going on for 15 years, looking at these 1 million red supergiants, waiting for them to disappear. And so their best candidate so far, now you can turn, and you can turn for a few clicks. So basically what you see on the left is this star in NGC 6946 in 2007 in the blue circle that the universe very kindly put there for us. And when you go back in HST again in 2015, the star is sort of like not there. So the original group classified this as a 25 solar mass red supergiant. I think more recently, we think this was a hotter star, more of a lower mass yellow supergiant, but that doesn't matter yet. Okay, the light curve is very interesting though. So basically the gray and the black are the Spitzer infrared, and then almost everything else is sort of visual wavelengths. There's some HST near infrared, but don't worry about those so much. Basically what you see is before late 2008, you just have this progenitor star moving along at its sort of supergiant luminosity of about 10 to the 5 L sun. Then it brightens by a factor of 4 or 5 in the optical, and you can see that peak around 2009. And then it dims by 5 magnitudes in the optical. Notice the y-axis switches to a linear scale at the bottom part. And then curiously, you also have in the Spitzer data, so the gray and the black sort of in the middle of the figure vertically, you have this infrared excess that continues and seems to be falling off in time. And so just from the observations, the progenitor has a luminosity of about 10 to the 5.63 L sun. And they originally said the temperature is about 3,600 Kelvin. Humphreys comes back later, says it's 5 or 6,000 Kelvin. We'll come back to that later. But then if you look at the bolometric luminosity sort of at late times, and I'm including the date 2024, because this is basically when the last two papers there, Beezer and Kachanik, each independently went back with JWST. And so this source is sort of still undetected in the optical, but there is an infrared source. And the bolometric luminosity is about 10 to 15% of what the luminosity of the star was before this event. Okay, and so Kishaloy found another one of these, I think last summer. So when I was getting ready to move to New York City, I was looking at this data and trying to understand MESA models. But okay, so this is interesting. So Kishaloy was actually doing a study of WISE data looking for mid-infrared transients. So he had developed this pipeline to do the difference imaging. And he finds this thing that you can see in about 2014. So the WISE data is the orange and black squares at the top. So you can see there's this brightening of about 50% in the mid-infrared. And then you have this dimming and this sort of power law fall off in the mid-infrared. And then simultaneously, all of the other points to the left, you're basically just marching along at the stellar progenitor luminosity. And then coincident with the mid-infrared brightening is you have this dimming in the optical. So all those red, teal, and purple points. And then you have this almost complete disappearance in the optical. And today it's just completely undetected in the optical, and it's just an infrared source. Okay, and so the just matching the SCDs in 2012, it looked like about a 10 to the 5 L sun yellow supergiant with a surface temperature of about 4,500 Kelvin. And then the remnant, again, has about 10% of the luminosity of the star, and the emitting region is maybe 20% of what the star's radius was. Okay, so clearly these stars did not have a supernova, but they must have ceased their nuclear burning, because how do you take a star and go from 10 to the 5 L sun to 10% of that, right? But in both of these cases, we saw some kind of low energy outburst that connects the star to this remnant. And so what I'm going to talk about on the chalkboard now is what are the ways that even without a rapidly rotating core, if you have a failed supernova, how can you still have a transient? Okay. Okay, so the first way that this can happen is I'm just going to call this, there's not a good name for this, so I'm just going to say you have a weak shock from neutrino mass loss. Okay, and so if you're below that sort of pair instability mass range that Matteo was talking about earlier, basically all of these stars go through a protoneutron star phase. The iron core at the time of collapse is about 1.4 solar masses, so you can exist as a protoneutron star at that mass easily. And so basically all these stars, the core collapses and you make this sort of hot protoneutron star. But of course it's cooling by emitting copious neutrinos. Okay, and because E equals mc squared, the energy that you lose from this core translates to a sort of mass loss in the core of about 0.1 to 0.3 m sun over a time scale that I'll call tau nu, which is like a few seconds. Okay, so you can imagine, I should have drawn this bigger. There's going to be some radius inside of which, where the sort of free fall time of the star, which I mean is the dynamical time, is the sound processing time, all within factors of a couple. You're inside here, the free fall time is less than this tau nu. And so those layers can just respond and they're going to free fall in and collapse and become part of the black hole. But then in this outer region, you know, the dynamical time of the star, or the free fall time, is actually much bigger than tau nu. And so from the perspective of these layers, it doesn't know yet that the core collapsed, but the gravitational field information travels at the speed of light. So what it knows is that suddenly the enclosed mass at every layer changed, practically instantaneously if you're sitting in the envelope. And so the envelope actually ends up being overpressured and gets a kick, and then you can have a sound wave, steep it into a shock, and maybe eject some of the mass at the surface. So let's look at maybe what that energy is. So first we want to know what the overpressure is. So originally, the star, you have a dPdr is minus rho gm of r over r squared. But then now, let's say dp prime dr is just very simply whatever the enclosed mass was before minus this delta m. And so this dp prime, if you just separate it into the two terms, rho gm over r squared, and then plus, because of the minuses cancel, then you have a rho delta m over r squared. And so this first term, right, this is just the dPdr we had originally. So that's what it's in hydrostatic equilibrium with. And then you have this extra piece, which is the overpressure. Okay. Now you want to ask, at each radius, what's the sort of little kick? Yes.
I'm sorry, I'm a little bit confused. So where exactly did delta M go?
So this is the delta M that you lose from the core due to this neutrino mass loss. And we're well outside that radius. So basically every shell out here where the free fall time is longer than tau nu, you just subtract from the enclosed mass at its radius the same delta M.
Oh, I see. Is this like mass is going to transfer into the envelope, or is this going to?
No, this is that you're cooling by neutrinos, so that neutrino energy is carrying away an effective gravitational mass from the core as E equals mc squared. Okay, okay. All right, so if you want to know what the little kick is, you know, each shell can sort of respond on its local free fall time or the sound processing time, this just sort of characteristic time scale. And oh, and I should say, let's define this piece, right? So see how this is little g? That's an acceleration. So that means this thing is also an acceleration. Let's just call that AR, okay? All right, and so you know that, I'm getting tangled in my mic. Okay, so this AR is just G delta M over R squared. And the local dynamical time or free fall time is just roughly this R cubed over G M. This is G M of R to the 1/2. And so the velocity that you can get is this acceleration times this characteristic time scale that this information can sort of propagate. Okay, and so if we just put that together, then you have a G delta M over R squared times this thing. And if you introduce a factor of M of R over M of R, you can write it in this nice way. Which is G, I won't do the algebra, which is just GM of R over R to the 1/2 times delta M over M of R. Okay, And notice that this piece is just the free fall velocity. So this is like the free fall. And delta M is much less than M of R. So that means the little velocity that you can get in each little shell is much less than the local free fall velocity. Okay, and so you're not like escaping, right? This is a square root of 2 related to the escape velocity. So this little pick isn't enough to locally unbind each layer because V is much less than V escape at that radius. Okay. Okay, but we can ask, let's look at the energy profile. So how much energy is in each shell? So let's just call this delta E of R. And let's just say this is 1/2 times the mass of the shell times this V squared. I'm going to go over here because I think it's hard to see if it's down there. Okay, so this M shell, you can estimate, is just a 4 pi R squared times rho, with the thickness of the shell is just the local scale height. And you can do some funny things where you say that this 4 pi R squared rho, this is dm dr, but that's also m over r d log m d log r. And then if you introduce another factor of r, then you, oh no, I'm not introducing that yet. So this is basically so that means this is d log m, d log r, m over r times h. Okay, so that's that piece. And then of course, v squared, we already said is this, but we're just going to square it. So you have a gm over r and you have a delta m squared over a big M squared. Okay, and so if you just multiply those and you do some simplification, what you'll get is that this delta E of R is 1/2 d log M d log R h over R times this G delta M squared over R. Okay, and so if you look at MESA models, what you'll see is that this is roughly 0.4. That's sort of the center of the range of values this could be. Maybe this is, 0.3 to 0.4. And then this R actually for red, yellow, blue supergiants and Wolf-Rayet stars. So what I should say is this is a decreasing function in radius. And so the largest value that this can have is at the smallest radius. But can I go all the way to the core and just take the radius of the core? Why not?
Is that stuff had already collapsed in?
Yes. So the smallest R I can get to is this one, which is where T free fall is roughly tau nu. That's the smallest R I can take because everything else free fell in. Okay, and so it turns out that this radius for all those progenitors I mentioned is about 10 to the 9 centimeters, which is in the carbon-oxygen layer. Okay, and so we can just estimate then for those values, if delta M is 0.3, then this delta ER at this radius of, equality, I don't know, I'll put a tilde over it, is about 10 to the 48 ergs. Okay, and I should say that the largest mass that you can lose by neutrinos is the case where you form the black hole as late as possible. So that would be the stiffest neutron star equation of state that you have. So you can keep emitting these neutrinos as long as you can, and then you collapse to a black hole. The lower limit is if you have a very soft equation of state and so you have a very low maximum mass of the neutron star, then you're going to emit less neutrinos and this delta M will be smaller. So emitting less neutrinos before you actually collapse to a black hole. And of course, once you collapse to a black hole, you've lost your neutrino source, so you're done. Okay, and so if delta M is 0.1, well, that's 1/3 of this. So that's a 1/3 squared. So 1/9. So it's about a factor of 10 smaller. So this delta E is about 10 to the 47 ergs. Okay. Now I just want to quote for you. So I already told you that basically the biggest sort of energy reservoir that you have is at this radius. And so you're going to be overpressured in this region. You make a sound wave. It accelerates down the sort of density gradient in the envelope, steepens into a shock, and then maybe you can eject some mass from the surface of the star. And so I'll just quote some results for you. Numerically, for different progenitors. So a bunch of folks have done this, and my favorite paper is this one, Ivanov and Fernandez. I think this was 2021. Oh, I lost my paper. Yeah, 2021. And what I like about this paper is that they self-consistently model using GR1D simulations, the evolution of the protoneutron star and collapse of the black hole, and then couple that to simulations where they've used the MESA model of the envelope. And so basically what they find, initial studies of this, they looked at the envelope and they just had some prescription for how this delta M changes with time. But they actually did the core evolution and the envelope evolution. And so this is my sort of preferred source for this. Anyway, so for different models, you can look at what's E ejecta, M ejecta, and E ejecta plus E recombination. I'll explain that in a second. And so for red supergiants, the ejected mass is like 1 to 3 solar masses. And they found energies of 10 to the 46. Can you read this? Okay, 10 to the 46 to 10 to the 48 ergs. The energies are less important than the mass here. For YSGs and some of their blue supergiant models, the characteristic mass loss is about 10 to the 2 M sun. And similar energies, 10 to the 46 ergs. This is the energy of the ejecta plus hydrogen recombination, which I'll mention in a sec. And then for some of their blue supergiants and basically all of their Wolf-Rayet stars, the mass loss is of order 10 to the -4 solar masses. And again, similar energies, 10 to the 45 to 10 to the 46, but somewhat lower because this energy is similar for all of the models, but the binding energies of these stars is very different. So the best way of having a transient is having the most sort of puffy, tenuously bound envelope, and that's in the red supergiant case. Okay, so I want to mention this E recombination because this is kind of super important. So, so this is going to come up a lot in the next half an hour, is that, you know, if you eject a bunch of hydrogen at some energy from one of these supergiant envelopes, this is basically like a type 2p, but scaled down in energy, right? So you send some kind of shock through, that shock breaks out. So you'll see some kind of, you know, shock cooling peak from the cooling of that material after shock breakout. But then now all of a sudden you've deposited energy in all those layers. And so this envelope is going to expand. And as it expands, it cools from the outside in. And so as it's cooling on the outside, your electrons are recombining with a hydrogen. The electrons were your source of opacity. So this recombination wave that's sweeping in mass coordinates through this expanding ejecta is also coincident with your photosphere, because that is where you're losing your opacity source. So that's what's setting the plateau for the type 2p. This would be very similar, but there's a really important caveat. So if this material is very radiation pressure dominated behind the shock, then this sort of photosphere or this recombination front gets pretty thin. So in my opinion, I think that if it's recombination pressure dominated, then you don't get to count the energy you get from hydrogen recombination in the energy you need to eject the mass, because a good chunk of those photons are going to be just free streaming to infinity, right? The recombination is happening in this really thin region. How are they that much coupled to the gas that they can help you basically eject the mass? And what a lot of people do at these energies, also in the common envelope case, is they just say, well, because like actually they didn't unbind any mass in their simulations, but if you add in the recombination energy, then this is the mass that you've unbound. Now I will say for my simulations, for red supergiants, once you're below about 10 to the 48 ergs, you're very gas pressure dominated. And then in that case, yes, this recombination layer starts to get broader. And so then maybe you have a region where the photons are still coupled to the gas, and maybe that can help you eject some mass. But when people just add this, there's some really important caveats there. And I don't think it's well enough understood, like how dynamically important, like what fraction of the recombination photons are when you're at this transition region between radiation pressure and gas pressure dominated. Okay, so that's just a side and kind of a pet peeve of mine, but I'm going to do a paper on this, so hopefully, yeah.
So I was going to ask, I mean, this hydrogen recombination energy should only also affect the outer envelope, right? Okay.
Yes. Well, yes. I mean, it's going to affect the region where you're closest to that recombination wave.
Right.
So in the beginning, it's the outside, but then this is sweeping in mass coordinates, right? Oh, and just to give you a number, that if you have 5 solar masses of material, and let's say it's all hydrogen, so like 13.6 eV per particle, then this is around 10 to the 47 ergs. So you can see that once you, if you have a very massive amount of ejecta, then you start to have, solar masses of material that can recombine, and then at these lower energies, the recombination energy will start to become important. Yes, Valeria?
Stepping back a little bit, so are we certain that we're going to form a black hole after this, or can we form a neutron star?
Sorry. Okay, we've already assumed that a black hole is going to form. This is a failed supernova. Okay, I mean, by the time all this is happening in the envelope, you've already formed the black hole. It's just while you were still, I should have drawn the picture that you're a proto-neutron star for a little bit, and then you collapse. And during that little bit of time, you emitted those neutrinos that gave you the mass loss that gave you this wave. But by the time this is all happening, you're way already a black hole in the center. Yeah, this is happening on much longer time scales. Okay.
So sorry, one more question. I'm also trying to conceptualize this versus the successful shock breakouts. So you're depositing energy via neutrinos, it's driving a shock. This is a
no. So wait, in the successful one?
And then this failed one.
No. The neutrinos are not coupled to this envelope. Okay, the hot protoneutron star is cooling by sort of neutrinos, right? So even with whatever's happening in this deep layer, that neutrino heating wasn't enough to revive the main supernova shock, right? Yeah. So that whole layer is going to fall in accrete and become part of the black hole. But the thing is, the envelope doesn't even know that any of that happened. Because the dynamical time is so much longer than this seconds time that it takes for this to collapse, right? And so the thing is all this inner stuff is going to collapse. It's not like in sonic contact with the envelope, but the envelope definitely knows when the gravitational potential changes. So it's just the change in the gravitational potential and this little wave that you get that propagates out, steepens into a shock, that is allowing you to eject some of the outer layers of the envelope. Okay, and I regret they have some nice time series where they show you basically the shock starts out very sort of tall in velocity. It's losing energy as it's climbing out of the gravitational potential well, but it's increasing in Mach number because the pressure is going down. And then it becomes a supersonic shock sort of right at the surface, and then there you can unbind some mass. Yeah, so it's not the neutrinos. It's just this instantaneous change in the gravitational potential that the envelope is aware of. It doesn't even know the black hole exists yet. Okay. Okay, so any other questions about this mechanism? Valeria?
So for instance, if I were to give you like a massive star,
Mhm.
how do I know it would undergo a failed supernova?
So this is a whole industry. And what, actually, I can show you this plot. Okay, so all of the folks who are working on, I didn't mean to do that, sorry. Let me go to this plot. So the short answer is like, we don't know. Okay, let me see if I can play this. Okay. Okay, so I think, so it used to be that people would say that, so there was this O'Connor and Ott study where they used actually the same GR1D code, and they simulated a bunch of massive stars through core collapse, having all the neutrinos and everything, this is in 1D, and seeing which ones led to successful explosions or not. Okay. And so there used to be this compactness parameter that everyone believed in, which was basically like the amount of, it was basically how dense the core was. It was just some parameter that they used. It was like at what radius do you go to enclose 2.5 solar masses? And then it's 2.5 solar masses over that radius cubed. Okay, it doesn't even matter. So people used to think that higher compactness cores were harder to explode, and then you would form black holes. Okay, but this has been sort of disproven, and instead it's this density gradient at the silicon-oxygen interface that came up during Jared talks last week. Okay, and so what I'm showing you in this plot is on the top is a collection of 1D simulations. The bottom is 3D simulations from Adam Burrows' group. And so the 3D ones on the bottom are remarkable in the sense that they've run for long enough to know which things really do fail and which ones do succeed. So, and these 1D models from Luca I like because, this explosion is really a 3D mechanism because it's not just a neutrino heating, it's actually the turbulent convection that you get from the neutrino heating that is really critical in allowing you to successfully explode this star. And so what they've done in these 1D models is they've come up with like a mixing length theory where they've parameterized the convection in 1D. And if you know anything about mixing length, there's this parameter alpha. And they basically tune this mixing length alpha to 3D simulations. And so what I'm showing you there is for two different sets of models, 3 different sets of alphas that they think are right when you compare to 3D simulations of this turbulence. And so the main takeaway here, so all the green points are successful explosions that for the most part leave behind a neutron star. And all the black points, this is a function of the 0 mean sequence mass, is examples of failed explosions where you form a black hole and the rest of the material is mostly still bound. But it's really important. This is really uncertain because, this is not monotonic nor single valued in terms of the initial stellar mass. And in fact, it depends really sensitively on the structure of the star right at the time of core collapse, namely how steep is this drop up at the silicon-oxygen interface. It looks like that in some of the models. And this cannot really be well studied in 1D. And so we don't know, like different stellar models produce different internal structures, and that entire internal structure determines the answer to this. So that's the long way of saying we don't know, but we would like to know. And this is actually why we care about the failed ones, right? Because when we see a successful explosion, we're just seeing all the ones where this was successful. And then you could try to guess, okay, how many black holes are there in the universe by comparing that to the star formation rate and the IMF. Like we don't really know how many massive stars are and what their distribution is mass is at the time of formation. And so what we would like is if we can also observe the failed ones, the things that form black holes without a supernova, then we have another observational way to probe the underlying distribution of black holes in the universe. Okay. Okay, so there's another way that you can make a low energy explosion. Okay, I'll erase that after. Okay, and so what I'm just going to call this is random angular momentum from convection. What I alluded to at the beginning is that these red supergiants and also the yellow supergiants are very slowly rotating at the time of collapse. And so people assumed that you form a black hole in the failed supernova. And then this envelope, because the star is really not rotating that much, all of the parcels in this outer envelope, the hydrogen envelope, are just going to fall in on radial orbits, fall in spherically. Quiescently, you're not going to have a luminous transient. But actually, these hydrogen envelopes are convective. So you form a black hole, and then you have all these parcels that before the collapse, they were on these totally random orbits, right? I mean, this turbulent layer is this random velocity field. So you have little velocity vectors going in all different directions. And what I can't underemphasize is the size of these envelopes. If we replace the sun with Betelgeuse, Betelgeuse's envelope would extend past Jupiter's orbit. And the convective structures occupy a large volume in this envelope. Like maybe you have 5 or 6 giant convective plumes in this huge volume. So even though in sort of like Mach number and pressure difference, this is a very small perturbation to hydrostatic equilibrium, these structures are very large and the moment arm is very big. But what you can imagine is now, instead of this stuff, you know, once I pull the rug out, like I take the pressure out the bottom, everything's going to collapse from the inside out. So this parcel that was on this trajectory is going to try to follow the path that conserves the angular momentum it had before collapse. And then maybe this parcel was already kind of radial, so it's going to go in. So 2 things. One is if this parcel was by itself, it would fall in, it could miss the black hole and just go back out. But the really critical thing is you have all of these things that are, this is a very dense fluid. So you have all these interactions and you can make shocks. So where these things are running into each other, you have shocks. And what's the job of a shock? A shock takes the bulk kinetic energy, right? And it converts it into heat. And so because of these interactions, because of all these shocks, you're able to sort of access this very supersonic infalling kinetic energy of this material and convert it into thermal energy and sort of kinetic energy of an outflow. Okay, but this is only important if, I'll say important if, the specific angular momentum of this material associated with convection is bigger than the specific angular momentum at the innermost stable circular orbit of the black hole at the ISCO. Or said another way, like who thinks in terms of centimeters squared per gram, unless you like opacities? I like to think of this in, I mean, I do like opacities, it's just a different context. Okay, so another way of saying this is you need the circularization radius of this material to be bigger than the radius of the ISCO. Okay, so let's estimate, like, is this true? Do we care about this? Okay, so let's estimate J convective. Okay, so the first sort of toy model of this basically you just consider it. So this was Elliott Potter with Daniel Laplané and a couple of other folks. They said, okay, let's try to make a local estimate of this. And And let's just consider one shell of sort of one scale height tall within this envelope. So just imagine you have this shell, it's at a radius of r, and the thickness is just your scale height. And of course, these are all convective. Let's say we want to estimate the number of sort of convective eddies that are in this shell. Well, the volume of the shell is just 4 pi r squared times the scale height. And just kind of for mixing length theory, the volume of an eddy is roughly a scale height cubed. So then the number of eddies, you can just divide the two. So this is a 4 pi r squared h over h cubed. And so this is just 4 pi times r over h squared. Okay, now the source of angular momentum, of the sort of mean angular momentum in each shell, is the mean velocities that are perpendicular to r, right? The radial velocities don't contribute to angular momentum, but the sort of theta and phi velocities do. So let's just write, so the mean v perpendicular to r, I'm going to call this VH just for horizontal, meaning non-radial. Well, this is roughly just the, so VH squared is roughly the mean velocity squared, right? If you have a velocity where all the components are the same, x, y, and z, there's like a square root of 2/3 here if you take 2 of the components. So I'm just twiddle, I'm calling it that. Okay, and then you want to compare this to the convective velocity. And so this is the RMS velocity. So this is the root mean squared. And so let's call this VC. So VC squared is just the mean of the square, right, that, okay? Right, if I take the square root, that becomes the RMS, so I'm squaring it, yes?
I probably missed this, but could you explain geometrically where the horizontal velocity is going again? Horizontal.
Yeah, I'm saying, so I'm saying V squared is VR squared plus V theta squared plus V phi squared. And so the horizontal component is this. You want, if this is your radial axis, let's say this is my velocity, I want what's perpendicular to this. And that would be the sort of magnitude of the vector from if you took the vector addition of these two, right? So it's the one that's perpendicular to r, because that's going to give you the angular momentum.
Thank you.
Okay. Other questions? Okay, so this, right, so now we want to know how are these two things related? The convective velocity I can sort of just get from a Mesa model, just from mixing length theory. So then I want to know what is VH compared to that? Well, you have a mean and you have an RMS. And so these are really just related. I'm going to write this and then I'll explain. So V convective squared is really just the number of eddies times this VH squared. And this might seem weird, but if you think back to your random walk, remember when we did a random walk, we assumed each little step was oriented in some random direction, and the size of each of those steps was your mean free path. And then we showed, I think we did this twice on the first day, that the sort of net displacement that you have is the square root of n times the mean free path. And basically, if you did the vector version of this and you wrote out this all the same math, you would get the same relationship. Because remember, you have all the dot products and then all the cross terms cancel because it's random, all of that. Okay. Okay. Okay, so this means that VH is VC over square root of the number of eddies. And then this is VC over square root of 4 pi. And this is H over R. Because I took the square root of the number of eddies. So that's why it's not H over R squared. Okay, so now we have the velocity we want. And so now let's say, okay, what's this J convective? Well, that's just like R times VH, right? The moment arm times the perpendicular velocity. And so this is like an R VC over square root of 4 pi H over R. Okay, and because specific angular momentum is weird if you're me, let's write this as the circularization radius. So R circ is this J convective squared over G and black hole. And that's from the fact that, where can I write this? I'll write it right here. This is another aside. Remember, the definition of R circ is what is the radius of the Keplerian orbit I would have for a given specific angular momentum. So it's basically this definition that J convex is defined to be R circ times V cap. And V cap, of course, just depends on M black hole and R. And so that's where you get this R circ. Okay. So then if I plug in this J convective squared, I get a VC squared over 4 pi, H over R squared. I'm introducing a factor of R because it's helpful because we know H over R from MESA models, where if I write H, I have to look up a bunch of things. Okay, and so this is over G and black hole. Okay, if I write right here, is that impossible for you to see? I'm going to erase these two little asides. Is that okay? Okay, because I just have one more thing to write on this, and then I want to start a new section. Okay, so we can estimate what this is. Oh, actually, it's a lot. Okay, I'll sort of here. Okay, so for a red supergiant, the convective velocity is about 10 kilometers a second. This H over R is about 0.3. And then the radius, let's say, is about 1,000 R sun. And then the mass of the black hole is 6 M sun. Okay, so in that case, you get that R circ is about 4 times 10 to the 10 centimeters. And this is about 0.6 R sun. It's pretty big. Okay, so now let's write the yellow supergiant case. So a yellow supergiant, okay, the convective velocity now is like a few kilometers a second. Oh, and if you think this is magic, I just happen to have a bunch of MESA models of red and yellow supergiants, and I literally just looked at the plot to get this number. So I don't like have internalized all numbers for stellar structure. So yeah, when I was a grad student, I thought postdocs like just knew all these things, but no, like I literally just looked at my MESA models. Okay, all right. H over R again is about 0.3. This is because we're interested in the hydrogen envelope in both cases. Now the radius is smaller, maybe up to about 500 R sun. And then again, we're going to take the same mass as the black hole. Okay, and so in that case, you get that the circularization radius, sorry, I ended up down here again, I write too big, is about 10 to the 9 centimeters. And this is 10 to the minus 2 R sun. Okay. For comparison, our ISCO for the 6 solar mass black hole is, so let's say non-spinning, so that's 6 GM over c squared. This is 50 kilometers. Right, so this indeed matters. There's no way that this hydrogen envelope can accrete spherically onto this black hole, because it's going to, all of this stuff is going to be significantly deflected from radial infall well before it reaches the black hole. And so we can ask maybe how much energy can we liberate with this material that reaches the circularization radius and, you know, has these shocks, gets turned around, drives an outflow. So let's estimate the energy. I'm not touching that again. Okay. Okay. Okay, so this is really simple because like the maximum energy that I can have, oh, let's write a title, let's estimate the energy. The maximum energy I can have is sort of my accretion energy at the circularization radius. So let's say E is G m black hole times the mass that reaches the circularization radius over R circ. Okay, and I'm going to pull some magic here, which is from simulations. I know that this accreted mass that actually reaches the black hole is about 10 to the minus 2 of the mass in the envelope. That only about 1% of the mass in each shell actually reaches the circularization radius. The rest goes into an outflow. You actually unbind about 99% of the envelope. And this I know from simulations. Okay, so given that, then for our trusty red supergiant, here the envelope is about 10 m sun. We said the circularization radius is about our sun. And then again, the mass of the black hole is 6 m sun. And I'm saying 6 m sun because this is sort of the cart leading the horse. But I know that because of these mechanisms I'm talking about today, the hydrogen envelope gets unbound and the black hole mass ends up just including all the mass up to and including the helium layer. And so that's about 6 solar masses, maybe a little less depending on your stellar model. Okay, right. So the energy here is 2 times 10 to the 48 ergs. And then for a yellow supergiant, here the envelope. And I should say I'm interested in these yellow supergiants that you've sort of stripped the envelope later at some point in its life. And so it indeed dies as a yellow supergiant because it has a low mass envelope. Yes?
Could you explain how you end up in binding? Like I understand that 99% comes from simulations.
Yes.
But why would you expect to unbind most of the envelope?
Because the envelope is extremely tenuously bound. The envelope of a red supergiant has a binding energy of 10 to the 48 ergs or less. So you easily unbind this hydrogen envelope because you have a very small amount of mass that is reaching this kind of small radius of an R sun, and it's probing the gravitational potential there. And because of these interactions, it's able to share that energy with the rest of the parcels of gas. And so you drive this outflow. And because the envelope is so tenuously bound, you easily eject most of this hydrogen. Yeah, does that answer your question? Okay, good, okay. All right, so these are these, so if you have a red supergiant in a binary, maybe it, yes, Larry?
Just to clarify, what is the source of the free energy here? Like, where is the
Gravity.
Gravity of the, sorry, like what is
Here?
Or, yeah.
This is just,
that's like a black hole, and then the other M is,
so this is, okay, so this is the mass of the hydrogen envelope. And and M accreted is that fraction of that actually reaches the circularization radius. And that's the thing that I'm just quoting from simulations, that I know that only about 1% of the mass actually accretes in the simulations, and the rest goes into the outflow. Okay, so here is the mass of the envelope is like a half a solar mass. So if you strip a red supergiant down to less than a solar mass of hydrogen, then it actually contracts and gets hotter because it becomes partially radiative, and then you will undergo core collapse as a yellow supergiant. And that's, again, one of those things that I just know from running a bunch of MESA models. I don't like magically know this from like Kippenham textbook or whatever. Okay, all right. So in this case, we said the circularization radius is like 10 to the minus 2 our sun, and then we'll use the same black hole mass, and you get an energy of about 10 to the 49 ergs.
Sorry, can I ask you
Yes.
another question? It's not super obvious to me that why in the yellow supergiant case and the red supergiant case, you are still doing 1% of your mass accreted. Like they seem like the envelopes are very different, like densities and masses and stuff. So maybe that number would also change.
It could, except that these simulations are dimensionless. And so, but you're right that if the density profile is very, very different than what I simulated in my dimensionless simulations, then the yellow supergiant case could be a little different. Yeah. And the density profile I chose in this, and the simulations that got this, was more the red supergiant case, because we were motivated by that first Kachanic event, which they said was a red supergiant. But actually, it turns out the progenitors of both of these things were yellow supergiants, and the progenitors of luminous red novae are often, of the brighter ones, are yellow supergiants. But yes, if the density profile is very different, then maybe this could be a little different. And that is actually a good segue, because in my simulations, I was simulating the red supergiant envelope, which is about like 840 R sun. So I did not simulate all the way down to the ISCO radius. And so, so from the simulations, so a common number. So what you do is when you don't simulate all the way down, like you have a sink in the center. So that mass is just going away. And unless you have some subgrid model for the black hole feedback, you know, as I change the radius of my inner boundary, my accretion rate is going to decrease. And a lot of simulations, they find that m dot scales of r goes as r to the 1/2. In mine, with, so that's a very different type of flow. In mine, so this would be like more disk accretion. So most people simulate disk accretion, where you have this kind of almost spherical but very turbulent random flow coming in. Oh, this should be a proportionality, sorry. I find R goes like 0.6. But you can imagine right here, like, so if I take, I'm gonna erase this. So this is a little aside. Right, so if I say that my energy is, okay, so let's say my accretion luminosity is like a GM, this m dot, over some R. Let's say, right. Okay, energy, I'm just going to get rid of time, GM. So M, now this is this dot M times delta T. So so let's say this is the radius of my sink in my simulation. Then I want to know what would happen if I put in our sink here. Well, this E goes as M over R. And so this goes, let's just take a half so that the math is easier. So this goes as R to the 0.5, and then you have an R to the 1 downstairs. So you have that the energy that you would get out, because I'm probing deeper and deeper and deeper in the potential as I'm decreasing R, would go as my sink radius to the -1/2. So if I am able, and the way that we get this in simulations is we just do a convergent study. I mean, this doesn't converge because it's the scaling law, but you just keep changing the radius of your inner boundary, and you see how m dot scales with radius. So this is sort of like local to the sink radius that I did, right? So I'm just looking at a few points, maybe factors of 2 bigger, factors of 2 smaller, and that's where I got that power from. And simulators who are working more on these accretion disk where the angular momentum isn't random, they find, similar powers. Okay, but the important thing here is if I was able to decrease this by a factor of 100, then that would be a factor of 10 upstairs, and you could have a factor of 10 greater energy. So these could end up being more energetic, but we don't know until we actually simulate this type of turbulent flow all the way down to the sort of ISCO, which hasn't been done. Okay, so let's talk about maybe what would be the observational signatures. Yes?
Good. Well,
Raj?
I wanted to ask how the timescales of this mechanism compares to the other one.
So, yes, right. So this is sort of dynamical times of the envelope. So I should say both of these mechanisms are going to happen. Okay. In the weak shock that you're getting that's climbing out of the envelope from that Lovegrove case. Oh, sorry. Elizabeth Lovegrove was like the first one to really calculate numerically the last thing I talked about. So the shock is you put in a bunch of energy at the beginning, and then that's climbing out. And because we're in this sort of weak regime, it's losing energy as it's climbing out of the gravitational potential. And so it's weakening as it goes and gets to the surface. This is sort of being driven over the infall time of the envelope, which could be a whole dynamical time of the envelope. But basically, this thing, you're constantly feeding it with energy and momentum. And so this is actually getting stronger with time. And I did some estimates, and it seems like both of these things for the red supergiant case reach the surface at about the same time. This thing dominates all the energy. But if you want to model the fallback accretion, which will be important when I show you, go back to this Kishale's event, you want to take into both because you want to know what is the velocity distribution in the ejecta for the late time light curve when you have sort of weakly bound fallback. Okay, but the first thing, right, you instantaneously make the sound wave that goes out. So that's going to propagate out in a sound crossing time. I think this, you can drive it for a dynamical time of the envelope because you just keep feeding this accretion because you have lanes that material keeps coming in. Okay. All right, okay, so the observational signature, so I kind of already said this, is that, now you've ejected a bunch of hydrogen just with lower energies than a typical supernova. And so initially, you're just going to have something like maybe something that looks like a type 2P, but the timescales are very different. So if this is just the bolometric light curve, this is that initial cooling, either of these shocks reach the surface. And then this is the plateau that you get that's mediated by the hydrogen recombination. But the really big difference here versus the 2P supernova case is that you've done no explosive nucleosynthesis here. So the light curve is just going to fall off at the end of the plateau. You do not have this nickel tail. Okay, and so I'll just, okay, so a couple of times these scalings for the plateau luminosity and the sort of duration from Popov 1993 have come up. So those are in the first 2 days of notes. I find that these scalings work pretty good down to about 10 to the 48 ergs. But what I'll just show you instead is light curves of these. Okay, so the top, so these are 1D radiation hydrodynamic simulations where I've taken a red supergiant, that's the top row, or a yellow supergiant, that's the bottom row, and I've just dumped in instantaneous explosions of these energies. And again, related to Viraj's question is that for these failed supernova with the angular momentum driven, probably the event will be longer than this because I think you continue to feed this energy for a bit. But for just instantaneous explosions, these are light curves and they look kind of basically what I've drawn. And so for the top case where you have these red supergiant envelopes with 10 to the 48 to 10 to the 50 ergs, you have durations of hundreds of days. That's on the right. The left side is the shock breakout. And so you can see it's a couple of days. So that's the same data. I've just zoomed in on the left. But then for the yellow supergiants, which are on the bottom, you have a lot less mass. And so for the same energy, the expansion velocity is larger, right? Because E is the ejecta mass times the sort of shock velocity squared. So if you reduce the mass, you increase the expansion velocity. So then the durations are much shorter and you have events of more like 100, less than 100 days, so more like tens of days. Okay. Okay, and so this would be like the initial transient that you get from this sort of initial expansion of this ejecta. But we know that there's going to be some marginally bound material that's going to fall back. And so you can ask, what would the late time signature be?
Okay.
Yes.
Just a question. So these like light curves are increasing, on the plateau.
Yes. Yes.
What's the reason behind that?
That I'm not super sure about. I think that I think it's because you're not super radiation pressure dominated, especially in those red curves. And what's happening is if you look at the opacity around the emitting region, it's not just electron scattering. You also have a lot of absorptive opacity contributing. And so I think because the opacities are different and gas pressure is actually starting to be important for those lower energies, that it's changing the shape of that from what we see in like simulations of 2Ps. Yeah.
I don't know if this matters, but we were seeing similar things. And there's also this difference, which may or may not be relevant, that the recombination energy itself is important, right? Potentially.
Oh, yes. So for the 10 to the 48 ones,
Marginal.
it's marginal. If I compute what I would get in hydrogen recombination from all of the ejecta, and I compare that to my radiated energy, so L plateau times the duration, the radiated luminosity is about 2 times the recombination energy. So in the paper, I kind of say that for 10 to the 48. I also did 10 to the 47 erg explosions of the red supergiants, and those, the gas pressure dominated by a factor of 10. And those, the recombination energy was twice the radiated energy. So I'm not showing those. I'm going to do those calculations when I have hydrogen recombination. Yeah. But yes, the exact shape of that could be affected by hydrogen recombination. So I think both of those things are starting to happen at lower
Just
energies.
as a reminder, in normal supernova, recombination mediates the photosphere, but it doesn't contribute to the energy budget.
Yes.
Very much.
Yeah, and as you get to these lower energies, and especially I think the events that you're going to talk about today, so the luminous red novae, especially with so the galactic population of luminous red novae, where it's lower mass stars that are merging, those definitely, the hydrogen recombination is actually powering the light curve. It's not just mediating the photosphere, which is very different from type 2P, because there the recombination, you just care, oh, it's just setting the photosphere, but all of the luminosity is the energy you dumped in the envelope from the supernova. The actual energy from the recombination does not matter. And I think that's also true at 10 to the 49 and 10 to the 50 ergs, just based on my simulations. Yeah.
You said that the energy from hydrogen recombination is going to account for similar plateaus in order to supernova. But
when I made that statement, I was talking about this hydrogen recombination mediating the photosphere.
Okay, but basically, I guess what I'm confused about is why do we still get a plateau even though there are 2 factors? First, the energy release plus the
it's kind of happening at the same time. So, right, because the electron scattering opacity is going away so if I draw the opacity, let's say as a function of R, maybe it looks something like this, where here all of the hydrogen is now neutral, and here you're still ionized. Okay, and the opacity in here is basically your Thomson scattering from the free electrons. So as the material is recombining, it is emitting photons. You're getting a 13.6 eV photon, and you're changing the opacity. So these things are kind of happening at the same radius. So you're still going to kind of get the same sort of plateau and fall off, but the exact slope of the plateau and how extended it is will depend on, at the low energies, the photons you're getting from here. Because you can imagine, right? You know, I have this thing going out, I'm the observer here. So I'm seeing the photosphere. So this is setting my L in photons, right? Which is what I'm plotting there. So that's the radiated photon luminosity. But let's say there's this layer where I'm having recombination photons coming out. Either they're interacting and heating the gas, or they're just free streaming to infinity. That's going to add to the luminosity. And the total luminosity I see is the photons that came from the recombinations and the photons that just came because this gas is hot and is emitting thermal photons. But it's kind of like happening, it's the same process that's making both, so they're like intimately related.
And you also like made a comment earlier about the energy, like the total energy budget that is responsible for ejecting the material. And what you're saying is that photons from the recombination, they will just go out without necessarily binding to the mass.
Yeah, so in the first thing, they argue that all of the recombination photons that you get basically get reabsorbed by the gas and help push the gas out and help you eject mass. And I'm just saying it's happening in this region at your photosphere. So it's really unclear how much of that energy you can put into ejecting the mass or not. Yeah, okay. Okay, so the last thing that I want to talk about is at late times. And this will be very short, very twiddle. And so I just want to point out this relationship to, if I have a shell of mass that has roughly the binding energy, maybe a little less, it's marginally bound. And so it goes out, right? All of its kinetic energy, so it's going to be slowing down as it's climbing out of the potential. So let's just do a point mass case, right? If I give a point mass not quite enough energy to get to infinity, it's going to go out to its little classical turning point where all the kinetic energy now equals the potential energy, and then it's going to fall back. So imagine I have this marginally bound shell. I put a little bit less than its local binding energy. That's going to go out, reach this sort of classical turning point, and fall back. And so all of the shells where you have some marginally bound material that wasn't ejected by this process is going to give you the late time accretion onto the black hole. And what's really cute, Eric Coughlin pointed this out to me, is that remember in the TDE case, you had that the orbital period goes as the semi-major axis cubed. And that gives you this t to the minus 5/3 in the fallback. I think Itai did that really nicely. Remember the right-hand side of that, the MDE or whatever it was? Well, if you imagine a shell going out and falling back on a free fall time, isn't the free fall time squared also proportional to that, I'll just call it the apocenter radius cubed? So for similar reasons, you end up with a late time t to the minus 5/3 scaling in the fallback accretion. Because remember, this just came from this, looking at the derivatives, same thing here. It's just
would be right if part of the envelope is unbound.
Yeah. So this is the, because like outer parts are unbound.
To get to zero energy somewhere, so you need to cross from negative
Yes.
energies to positive energies, then you get this.
Yes, and so what I'm arguing is that these low energy injections that I was talking about, there's always going to be some radius inside which you didn't quite have enough energy to unbind and get to affinity. So you're going to probe where, and there's inner layers that are bound, right? So in these cases, you do have this transition from very unbound to bound. And so there's going to be this radius where the energy is about 0. Yeah, because you need to be around that radius for the MDE to be, yeah. Okay. Yeah, that's a very good point.
Wouldn't-
I was
wouldn't
stressing
this-
about this last Tuesday and then I figured it out. Yes. Yeah.
Wouldn't this be in X-rays rather than?
I think
optical?
it would take a very long time to see X-rays because you have basically a very quasi-spherical distribution of like solar masses of material, but at very, very late times. Then maybe you could see some X-rays. In these two failed supernovae, we haven't seen X-rays yet, but the sort of column depth of hydrogen that you still have really depends on the velocity profile that you assume. And actually, I don't remember if there was anything else I was going to write right here. Okay, so one thing I want to point out is that if m dot is bigger than m dot Eddington, then L is independent of mass, m dot. And I'm glad you two are here because you can tell me all the ways that this is wrong, but this is the way that I've been thinking about it. Okay, and so I want to show you why that's true, or possibly. So you can write down, so if you have a spherical accretion, then you have some radius where the photons become trapped in the flow. So you can imagine at the surface of the fallback, maybe they can diffuse out really easily, but as you're falling in kind of very supersonically to the black hole, there's going to be some radius where the diffusion time of the photons trying to go out to larger radii is longer than the free fall time from that radius as it's falling in, okay? And so you can write down what that radius is, and so that's just the trapping radius. And if you just write where it is sort of T advective, which is, this would be like R over V free fall for the parcel, is equal to the diffusion time. Then you'll get that the trapping radius is kappa m dot over 4 pi c. And then you can say, what's the accretion luminosity at the trapping radius, right? So when I say accretion luminosity, I'm saying the luminosity that's being generated from this m dot reaching some r. So this would be, so the luminosity at the trapping radius, this would just be g m black hole times m dot over r at the trapping radius. So this is g m black hole, m dot, and then trapping radius downstairs becomes a 4 pi c upstairs and a kappa m dot downstairs. And so the m dots cancel out. And so the luminosity at the trapping radius is basically 4 pi c g m black hole over kappa. Does this look familiar to anyone? Does it have a name? Yeah, so basically your luminosity is Eddington at the trapping radius. And so the idea is if my m dot is very large, you know, when I have this spherical infall, I have turbulence as my sort of dissipation mechanism, turning this energy into heat, that if m dot is bigger than m dot Eddington, then I just shine at the Eddington luminosity, and L does not care about m dot. So if I want the luminosity to fall off like a t to the minus 5/3 with my m dot, then I need that my m dot is less than m dot Eddington, so that L can become proportional to m dot times some efficiency factor. Okay, and so this idea sort of allowed us in this failed supernova candidate to use all of the data that was available. So what Morgan did here, okay, so the rest is sort of slides. if you want to turn it around comfortably. So what Morgan did, okay, so this is from that Day et al. Paper, so the failed supernova candidate in M31. And so what Morgan did is so for one thing, I should go back, using this data, we kind of know what the progenitor was. Oh, I was going to write these things down, but I won't. So basically, the best fit MESA model to this sort of pre-explosion star is a 5 solar mass yellow supergiant with about a 0.3 solar mass envelope, okay? Radius of 500 our sun. And so we had so there was no optical outburst here. So that constrained the possible optical outbursts we could have. We also had this information on the progenitor, and then we have this information of the time after which the bolometric luminosity starts to fall off as a t to the minus 5/3. And so basically what Morgan did was come up with a sort of self-consistent but kind of twiddle model to explain the bolometric light curve. So the black points here at the bottom of this plot, this is the bolometric luminosity that you would get from all of those data points that I would show you. And you can see that the luminosity is roughly constant up to about 1,000 days, and then you're falling off as this power law. Okay, and so what Morgan did is he assumed the top equation there is that you eject all of this sort of marginally bound material with a distribution of velocities. So V goes to R as some power, ended up not being that sensitive to that. But then, as material is falling back, it's hitting this angular momentum barrier, because indeed, even this material that was sort of going out has this sort of convective structure. And so the idea is that you have this little bit of angular momentum. So you hold things up sort of at the circularization radius, that gives you that 10 to the minus 2. But then we know that M dot I measured in my simulations goes as, R to the 0.6. And so then that would give you that the M dot reaching R ISCO is about 10 to the minus 3 times what actually reaches the circularization radius. And so if you put those things together, you get these diagonal lines. And so this is assuming different energies for that yellow supergiant progenitor, where the normalization of that velocity profile was set so that it gave you the correct total energy. And one thing I want to point out is the pink dashed line is if this was a red supergiant progenitor, and so the horizontal line is the sort of Eddington rate, okay? So you need these diagonal lines to be below that heavy dotted line if you want, the gray line, that's the Eddington, if you want the luminosity to follow the accretion rate. And so what you see is for the hydrogen rich, I see. No, that's not what I want. The orange line is if it's a red supergiant, you can see that orange line is like never going to intersect, like for thousands of years that you're going to stay super Eddington. And so you shouldn't see this fall off. But the thinner lines, so the green and the brown, that's for a 10 to the 49, sorry, it's hard to read, and a 10 to the 48 total energy explosion. But then the fallback luminosity that you would get is sort of similar to this tail that we see in the bolometric light curve. And so modeling the progenitor and the outburst and this fallback accretion, it seems like this was a 5 solar mass yellow supergiant that had a explosion of 10 to the 48 to 10 to the 49 ergs, and it only ejected about 0.1 solar masses of material. Well, 5 minus 0.1 is a lot bigger than the mass of a neutron star. So this thing would have formed a black hole. And so we think that this is an example of a black hole born in one of these failed supernovae. Okay. So I'll just wrap up sort of verbally in the sort of context of LSST. Is that, I have a plot. Sorry. I added some slides yesterday. Okay, so this is plateau luminosity versus duration. So the gray points in the background, those are those light curves I showed you earlier. The ones on the right are the red supergiants with 10 to the 50, 49, 48 erg explosions. The ones on the left are the yellow supergiants. This blue point with this wide error bar, that is the luminosity of that first failed supernova event discovered by the Kachanic group. And then the duration is very poorly constrained between 3 and 11 months, just because they had very low time resolution of their observations. And then the pink square is what the model for the M31 event would give you in the luminosity and duration. And then the purple diamond is sort of the corrected progenitor that Morgan also did in the analysis from the M31 event for the Kachanic event. So that's basically what the optical outburst would be for those two events if the Morgan's model is correct. But what I want to point out, and this segues into this afternoon, is those 3 black points are luminous red novae with supergiant progenitors. And in sort of photometric space, the durations and luminosities of these things are in very similar parameter space as these luminous red novae. And so Rubin is going to see about 1,000 times more luminous red novae than ZTF. And so there could be a lot of variety of low energy ejections of hydrogen from these stars, even by some of the mechanisms that Matteo talked about earlier, that we should see in the Rubin data. And they're not all going to be stellar mergers. And so one of the really key ways that we think, one of the key reasons why we don't think these 2 failed supernovae are stellar mergers is because we had data on the progenitor going back years. And if you have a stellar merger leading to a luminous red nova, you see a brightening of the progenitor over years leading up to the transient as the binary is starting to interact and you're ejecting mass. And so we did not see that in these 2 cases. And that was like a really big reason why we argued against the stellar merger scenario. Also the fact, how do you merge 2 stars and end up at 10% the luminosity of the progenitor? That's a big one. But Rubin is going to be staring at these stars and giving us this nicely cadenced data to see what were these massive stars doing before these events. And so to differentiate this variety of transients that aren't supernovae, but are in this lower energy regime, we really need to know what was the star doing before the event to help add to our model in order to interpret these transients. Okay, and so that's all I have.
This is very exciting stuff. So Andrea, do you understand correctly that you think you can measure the mass of the newly formed black hole from determining, the added luminosity of the thing?
No, I think that's hard.
Because with the case you told us.
Because there's some efficiency between the luminosity and the M dot. Morgan picked some value for that gray line. I don't know exactly what that is.
You wouldn't make the claim that that thing formed a 4 to 5 solar mass black hole. Right in the gap, by the way.
Oh, no. Okay, so what I should say is that all of this stuff says that you should have black holes in that gap. I did not include the plot. I really wish I did. I remember like in the middle of the night last night, and then I forgot this morning, is that if you take a bunch of stellar models up to 35 solar masses, if you if you collapse the whole star, including the hydrogen envelope in the failed supernova, then all of your black holes end up above the lower mass gap. And Anna, I'm so sorry I will show you this plot later because this is like key for gravitational waves people. But what I'm arguing is that in these failed supernova of these red and yellow supergiants, you always lose the hydrogen envelope and then you accrete up to the helium layer. And so that would just totally populate this lower mass gap. And whether whether the helium core is 4, 5, or 6 solar masses depends on what you use for your overshoot parameter during hydrogen burning. So, but I would argue that there isn't a lower mass gap. Yes.
So I think it's still written over there. You use the convection in the envelope to estimate the circularization radius.
Yes.
And then you said out of simulations, which I'm not sure what's included in them.
Yes.
Some fraction of that went to the circularization radius. Can I estimate that by saying that the energy released, the gravitational energy released, of the accreted material, basically G M black hole M accreted over R circularization equals the binding energy of the envelope. So when you have accreted enough material that you released enough energy to unbind the envelope, this is where the accretion starts.
That's a very good point.
So it will be quite different between those two cases, because
Yes.
the ratio of the R circularization to R of the envelope is very different between the RSG and the YSG cases.
What I will say is, again, this is from, like, once I know that what the simulation result is, it's hard to forget. But what I will say is that, and I regret that I don't have a movie, that you basically have all the material that sort of reaches the black hole first is the already cooled streams from the convection, because those are coming in with some radial velocity. And then mixed in with that, so this is before collapse, you have these hot, slowly rising plumes that occupy a huge volume. And what I see in the simulations is that once you start the collapse, those streams that had a little bit of a head start are the ones that reach the black hole. And then, but you have all, and then that is just extra heating all these plumes that already were rising. And so this accretion is happening in these very narrow channels where you're still able to probe the black hole. And actually what happens is the envelope is formally unbound way before you turn off accretion. And so, like in simulations, these are the numbers I get if I extrapolate my outgoing shock to when it reaches the surface of the envelope. But that's really a lower limit, because there's no reason why that should shut off accretion, because I have all these streams that were already falling in, because this is, even though it's on average very spherical, because of this random directions of all of this turbulent angular momentum, you're able to actually keep feeding the black hole well long after you formally unbind the envelope. So then I think you can equate the two things. Yeah. He just said good, Brian.
So I had a comment and a question. So.
Okay.
So the comment is, yeah, I like your analogy here, and in fact I think of these core collapse. You know, this is the same argument as to why I think TDs are. It's so difficult to get mass in the black hole. I think of, you know, a core collapse is you can almost think of the infalling star as a bunch of elliptical orbits, but they've been phase mixed.
Yes.
Unlike in a TD where they're all organized.
Yes.
Until something happens and then they get phase mixed. So for the same reasons, I think that black holes are fussy eaters and TDs. Now, whether that matter gets unbound or not, eventually creeps fine.
Yeah.
But anyway, that was just a comment. Then I guess the other I guess is also a comment, but just you're asking Rem and I how to punch holes in this argument about L being limited to L Langton, because of course there are things like GRBs.
Well, so I think if you have, okay, so almost every case of black hole accretion that people are looking at is where you have a constant angular momentum direction of the stuff that's falling in. Like, right, if you're rotating, I could have a different angular momentum in sort of each radial shell, but it's all facing the same direction. And so, yeah, you can definitely be super Eddington if everything is flowing into a disk, right?
But even super Eddington disks don't necessarily radiate super Eddington.
Okay,
but
fine.
But the point is, though, that you were saying the m dot goes out off as a power law, right? R to the 1/2.
Yes.
And so if you say GM, if you say the released energy is GM m dot over R,
yes,
that's actually growing down to the whole right.
Yeah.
So if you say that the luminosity source is not direct luminosity from the trapping radius,
yes,
but is energy that is released closer to the black hole that goes out in a jet or a wind and is collides with something, then you can get something which is much brighter than Eddington.
For sure.
And I think, and I agree with you, rotation facilitates a defined direction for that outflow, which may not be present in these systems. But I don't know if you can completely exclude that there's some feedback, right?
There definitely is. And I think, but this thing is changing direction on very short time scales. Like, I mean, as one parcel is falling in to the black hole, the angular momentum is ordered, but at larger radii, you're feeding this thing that's changing direction. And so this is like Noam Soker's thing with the jittering jets. Okay, so he was very excited by these results. I don't think all supernovae are jets, but I think in this case, yeah, you can have all these outflows happening at small radii, but for the most part, you're surrounded by this big, puffy, almost spherical thing that whatever's happening, I think it's all gonna get reprocessed
It
by
may
the
be hard
envelope.
to- Yeah, it may be hard to get out, but.
Yeah,
but
yeah.
you can't, my point is you can't have a super Eddington
Okay, yes,
flux of
thank you.
energy in
Yes,
small scales that
Yes.
in principle, you know,
yes,
this is how super Eddington winds
yeah.
can make moderately super Eddington winds.
And then in that case, you're not really limited by the trapping radius, I guess, because,
It becomes a, yeah, it has
It's
to
a
become a
different-
trapping radius and some kind of outflow. then,
yeah. Okay,
But I know, I agree, I think it's,
okay,
this is quite plausible.
okay.
As an FYI.
Okay, I think, yes, I think you're right. So time for lunch. Let's thank Andrea again.